With the first presentation of the today's session. The presentation number 3355, Carbon Governance and Distribution Vehicle Energy Choice, a distribution network model and study in the consumer electronics sector. Please. Are you ready?
Okay, yes. Okay. Good morning, respected professors and fellow researchers. My name is Wang Zibing. Today, I'm delighted to share my research, Carbon Governments and Transportation Vertical Energy Choice, a case study of the community's electronic. My presentation will cover 5 core sections: research background, feasibility study, model construction, research and the discussion, and the conclusions and the future prospects. Firstly, let's start with the research background. Global climate change by the IPCC is a major challenge worldwide. Countries have rolled out the carbon governance policy. The global consumer electronics market hit the $1 trillion in the 2023. It boosts China's manufacturing, upgrade, and carbon reduction, becoming a key area of the future research applications. Current research focuses on the 3 aspects: the deliberation of the digital economy, macroeconomic and the global value chain upgrading, and the carbon emission challenge in the industry. Based on this, my research has the 3 clearly objectives. Firstly, build the multi-scenario models to simulate the impacts of the different carbon policy. Secondly, explore how carbon governance intensity affects logistics, workload, and the energy structure transformation. Thirdly, evaluate policy applicability and find the optimal carbon governance range of the consumer electronics. Next is the feasibility study, including the practical cases, scenario foundation, and the scenario design. For practical case, we review the 3 typical global carbon governance practicals. Finland adopted a dynamic carbon tax, with the tax rate rising from the 7 to 85 per megawatt energy switching. The EU implemented the ETS cap and the trading system, with the annual decline in quotas and the flexible trading. The California used a strict emission cap plus ZEV regulations, reducing transportation emission by the 13%. The theoretical foundation covers 3 dimensions: operational optimization of the low-carbon logistics, effectiveness of the carbon pricing process, and the integrated government design. Existing studies confirm that carbon governance and the policy can significantly reduce the emissions. And finally, we set 4 scenarios: baseline, carbon tax, carbon trading, and the carbon emission cap, corresponding to real policy practicals worldwide. Now, moving to the model construction. We built the distribution network with Beijing as the original and the 36 demand nodes, covering 9 product categories. We set 2 vertical tabs with the 50 free setting 4 vehicles. We also made reasonable assumptions, such as the 8-hour daily working time, Odin completed with 3 days, fixed demands, sufficient in inventory, and no equipment fails. And this is symbols description. And we build the 4 scenario models with different objective foundations. All models follow the same basic operation constraints, ensure that the comparability of the results. Now, the core part, results and the discussion. We analyze the 3 key dimensions. Firstly, the dollar impact of the policy intensity. Compared with the baseline, all policies achieved huge emission reductions. For profit, the carbon trading increased the profit by 8.77%, while the carbon tax and the emission reduced profit also. All scenarios keep the fulfillment rate above 95.74%. Secondly, the vertical and the energy structure transformation. The carbon tax almost eliminated fuel vertical elimination. The emission cap used a mixed fleet. Carbon trading widely adopts the clean energy vertical. Total energy cost adjusted from the baseline to the carbon trading. Profit the flexible carbon prince improves energy efficiency. Thirdly, impacts on the product structure and the service level. Carbon policy shift distribution to high profit products. All scenarios maintain a high fulfill rate over the 96%, and the carbon trading minimized the impact on the service. Finally, conclusions and the future prospects. In these parts, we find the 3 findings. The firstly is that the all carbon government's policies promote the transition to clean energy vehicle in the consumer electronic distribution. Second, the conservative carbon tax has the best emission reduction, but it caused a large profit loss. Stringent emission cap is not optimal. Thirdly, the moderate carbon trading achieves both emission reduction and the profit growth, making it the most suitable strategy. And in the policy recommendations, enterprises should give priority to the carbon trading mechanism, and the government should profit the moderate carbon trading supplemented by the tiered carbon tax and the low carbon set for the low margin products. In the future and the limitation, we didn't concern the vertical subside and the cross-border logistics. Future research will end the subside factories, expand to the global supply chain, and integrate the carbon boarding traffic. And this is the references. Okay, overall is all my presentations. Thank you for your listening. I seriously welcome your question and value comments. Okay, thank you.
Thank you for your presentation, dear colleagues. Are there any questions on this presentation? Yes, I can see it, please.
Yes, I have a question. Thank you, Mr. Wang. So why is the carbon trading scenario considered the best carbon governance strategy for the consumer electronics distribution network?
Okay, thanks for your question. And I think the carbon trading is the most effective policy because it balances the profitability and the emission reduction Unlike the carbon tax, it doesn't not impose high direct cost, and unlike strict emission caps, it provides the greater operational flexibility. The results show that carbon trading increases the profit by the 8.77%, while recording the emission from the 71,499 to the 313 ton, with the fulfillment the rate remaining above the 95%. Therefore, it achieved both economic and the environment goals simultaneously. Okay.
Okay, thank you, Mr. Wang. Thank you.
Thank you. Any other questions? No, that your presentation is over. Thank you. The next one, presentation number 3362, Digital Transformation and Green Supply Chains, Mapping the Knowledge Structure and Research Evaluation, 2016-2025.
Thank you, Chami. I'm author, Tao Xin. Now I share my
Welcome.
representation. Thanks for Casey. Thanks for Professor Zhang. Thanks for you. Yeah. Now I share my representation. Wait a moment. Okay. Wait a moment. Wait a moment. Okay. Wait a moment. Can you saw my representation?
Yes, please, let's start.
Okay. Thank you. Good morning, everyone. My presentation is about the digital transformation and green supply chain. This study maps the knowledge and research evolution of this field from 2060 to 2025. The focus is the combination between digital transformation, green supply chain management, circular economy, and sustainable governance. Okay. This study starts from a clear gap. Digital transformation and green supply chain management are both important, but the literature remains fragmented. Therefore, this study has two research questions. Question one is what intellectual framework links DT, digital transformation, and GSCM, and how are digital technologies connected to sustainability concepts such as the circular economy. Question two is how has the research field evolved over the past decade, and what key issues are likely to shape future research directions? So I use literature analysis method, use BBD-Shany and Vosviewer to analysis method. The data were collected from Scopus. The screening process followed Prisma. The initial search retained more than 90,000 documents. After filtering by time, subject, area, document type, and source, 1,700 studies from 2060 to 2025 were included. In my research, my classmates have asked me, why are you only collected this resource only for Scopus? You should collected some resource from Web of Science. So I have checked now existing literature have pointed out The data were retrieved from Scopus database due to the broad coverage of reviewed journals and rich BBD graphics, matter suitable for large-scale mapping studies consisted with established bibliometric particles. Scopus were selected as the sole data source to ensure methodology consistency. Okay, I continue. Okay. This Prisma map, everyone you can see. Okay. Continue. The data set shows that this is a relative new but influential field. It has a high annual growth rate and a high level of international collaboration. The publications are mainly in green economy, supply chain operations, and digital management journals. The left figure is Voss viewer, came from Voss viewer analysis. The Voss viewer keyword network shows 8 thematic clusters. For this presentation, the main message is that these clusters from 3 dimensions: digital technology, sustainability governance, and secure supply chain operations. The Voss viewer software analysis mainly use the author keyword, and the all selected article, and use this author keyword and to analysis, and find now have 8 semantic clusters. This map is analysis from Bibli Shani. This semantic evolution shows 3 stages. The field first explored the link between environmental goals and single digital technologies. It then moved to deeper applications of blockchain and machine learning. In recent years, the field has become more integrated and focused on digital green transformation. The first stage from 2060 to 2090, the second from 2020 to 2022, the third stage from 2023 to 2025. Okay. This map also came from the analysis of Bibli Shani. The findings can be summarized in 5 points. The 5 points. Sustainability is the central theme. AI and machine learning support data-driven decision-making. The circular economy provides the conceptual anchor. Blockchain supports transparency. Digital twins and Industry 5 are important future directions. In conclusion, digital technology should be viewed as strategic infrastructure for green supply chain transformation. For managers, this means strong data infrastructure and cross-functional integration. For policymakers, this means incentives, green finance, and shared carbon data platforms. Thank you.
Thank you for your presentation, dear colleagues. Are there any questions? for the presenter, for the speaker?
Yes,
Please.
yes, Professor and Dr. Xing, and I want to concern about your strategic thematic map shows that the sustainability and blockchain and Industry 4.0, machine learning, and so on are located in different positions. And how does this structural relationship show that the digital transformation and green supply chain management research is moving from the isolated technology adoption to an integrated framework combining the digital with the green governance? Okay, thank you.
Thank you for long timing. I'm sorry for have a little bit anxious. Uh, the strategic map is useful because it show not only important topics but also their structure positions in this field uh, in the research field. In figure 5, this figure sustainability appears as a basic theme. This means that it is the core research context of this field. Industry 4 and a circular economy from a transitional core. This shows that digital technologies are increasingly combined with resource efficiency, circular production, and sustainable supply chain management. Blockchain, machine learning, and digital twins represent different levels of technology application. Blockchain focus on transparency and traceability. Machine learning supports prediction and manufacturing optimization. Digital twins show future potential in supply chain monitoring and predictive maintenance. Therefore, this relationship so that the field is no longer focused only on the adoption of only a single technology. It is moving towards the integration of digital technology, green supply chain management, and circular supply chain operation. This supports the main conclusion of this study. Digital transformation and green supply chain management research is moving from fragmented technology studies toward integrated digital green governance framework. Thank you.
Okay, are there any other questions? No, thank you. Your presentation is
Thank you,
finished.
Chan. Thank you, Professor Zhang.
The next presentation, number 3364, optimizing resource allocation in food recall logistic networks through multi-objective location routing problem models.
Yes, professors, can you see my screen? I will
Yes.
show it. Is that okay
Yes.
for you? Okay.
Yes.
Okay, I will start. Good morning, everyone. I'm Liu Feiyan from Guangzhou City University of Technology. And today I will present our work on multiple objective location routing optimization for food recall logistic networks using input genetic algorithm. For the background, food safety indicators continues to pose serious health risks worldwide. When defective food products enters the market, an effective recall becomes critical, not only for protecting consumers, but also to fulfilling corporate social responsibilities and regulatory requirements. A well-designed logistic network responsibility ensures that records are precise, comprehensive, timely, and cost-effective. The food recall logistic will face two fundamental questions: where to locate the recall processing centers and how to plan the transportation routines. These two decisions are strongly interconnected. Moreover, food recall have unique challenges. Because defective food can be hazardous, time control is very strict. But at the same time, logistic costs greatly influence recall decisions. This creates a complex multi-objective optimization problem. So, to address this, our study had three main objectives: to establish a multi-objective RLP optimization model for food recall logistic, and to propose an improved genetic algorithm to solve the model, and third, validate the model and algorithms through case simulations. Our model describes a two-stage reverse logistic process. In the first stage, the defective food products are collected from the demand points to the such as wholesalers or retailers, and to transport to the selected recall logistics centers. In the second stage, the products are consolidated and shipped in bulk to the food production enterprises. The system balances timeliness and cost efficiency. To make the problems tractable, we made several key assumptions. For example, we ensured road transportation only because recalls typically occurs within national borders. There are no transfers between local recall centers, and we do not consider loading or unloading times. These conceptions allow us to focus on the core location and the routing decisions. Now let's show you the mathematical formulations. We have two objective functions. The first minimizes the total recall time, which includes travel times from demand points to centers and from centers to the food plant. The second minimizes the total cost, including fixed cost for opening centers, departure cost for vehicles, and transportation costs. Both are minimized simultaneously. Several constraints must be satisfied. These include capacity limits at each recall centers and for each vehicle, parts community, subtour illuminations, and the logic relationship between open centers and vehicle assignments. All decision variables are binary. To solve this multi-objective model, we use an improved genetic algorithm. We convert the two objectives into a single weighted sum objective. The algorithm features a four-segment coding encoding scheme, adapted mutation rate, multiple point crossover, and a specialized selection method to prevent premature convergences. And you can see from this picture, the diagram shows one example of a chromosome from our input genetic answer. It has four colored segments. The red indicates the record demand point ID. Green is the signed collection vehicle ID. Blue is the record processing center, and the yellow is the long distance truck, which is from the record centers to the food plant. Together, these four segments defines a complete solution for the location routing problems. And the algorithm proceeds are as follows. We initiate the population, then we calculate the fitness, and the fitness we use the parameter functions to converge. We calculate the fitness after dimensionless normalization and weighting. Next, we perform selections, crossover, and mutation as the traditional genetic algorithm. And the mutation rate starts high at 0.08 to explore widely, and later decreased to 0.01 to converge. The algorithm stops at 300 generations and outputs the best solution. We tested our approach on a realistic case with 35 record demand points, 4 candidates locations centers, and 1 food processing plant. 10 patrol vehicles are used for the collection stage, and the paper helper provides the full tables of the coordinators. For the result, the result shows that 3 out of 4 candidates, no, here 1, 2, 3, candidates centers are activated, and the routing follows a cluster-based approach. So nearby demand centers were gathered together from the food to the food plant. The 2-stage process, first collecting and then bulk transporting, and then greatly improves the efficiency. As shown in Figure 2, the best fitness value stabilized after about 150 generations. The population mean stays very close to the best solution, indicating a good balance between the exploration and exploitation, with equal weights on time and cost. The algorithm converged smoothly here. And we run the algorithm 10 times with different random seeds. The standard deviation is below 1.5%, demonstrating strong robustness. Parameters sensitivity analysis shows that increasing population size beyond 200 or generations beyond 300 bring less than 2% improvement. So our chosen settings are nearly optimal. Compared to the traditional ad hoc methods, our approach reduces the average response time by 28%, down to 4 to 2 hours, and total recall cost by 24%. These gains come from better facility location, optimized vehicle routing, and an adaptive mutation strategy that avoids premature convergence. And to conclude, we have built a multi-objective location routing planning models for field record logistics and proposed an input genetical algorithm with 4-segment encoding and adaptive mutation. In a case study, 35 record points, we achieved 28% time reduction and 24% cost reduction. Of course, this study has limitations. We assumed a single product type and deterministic transport times. Real-world records are more complex. In the future, we plan to extend the model to multiple product type, different emergency levels, uncertain transportation times, and multimodal transportation options. And thank you for your attention, and I'm happy to answer any questions that may you have.
Thank you for your presentation. Dear colleagues, are there any questions? I can see one, please. We cannot hear you probably because of the microphone. No sound. No.
Sorry, we can't. Okay.
盛楠，你的话筒没打开，你的话筒没打开，话筒。
No sound, unfortunately.
Put on your microphone. No sound.
Maybe you can use your smartphone to connect. But and meanwhile, I'll ask you another question. Okay. Tell me, please, why is fast logistic important during a food recall? Why is it important?
Yes, thank you for your question. Because the defective food, some food hazardous, and it will influence the public. They will, if there is a safety problems, and the public will get panic, and it did a great damage to the brand. So the planter enterprises are very curious about the food security, and they should make sure the safety of the food never be input or influenced by other people's. So they wanted to record defective food to make sure they can control the whole circle of the food distribution. So it is based on the curious of the public.
Yeah, it's a really important topic. Any other questions, dear colleagues? If no, so thank you for your presentation. We will move to the next one. Number 3367, UAV route optimization for rural logistic considering energy consumption and time window constraints.
Hello, good morning, everyone. And today I will presenting our research titled UAV Route Optimization for Rural Logistics Considering Energy Consumption and Time Window Constraints. Our research address a practical challenge in the last mile delivery of rural areas, and we propose a novel model and algorithm to solve it. Let me walk you through our work. Here is the structure of our presentation.
Excuse me, I interrupt you. Can you open full screen mode, because we cannot see that you change slides. Yeah, it works. Sorry, continue.
Okay. I will cover 5 parts. First, introduction and motivation. Rural logistics in mountainous regions face 2 core challenges. First, the complex rural environment. Settlements are highly dispersed and sparsely distributed. The terrain is mountainous with limited road accessibility, and the conventional delivery methods are both costly and inefficient. Second, the challenges of UAV deployment. Geology consumption varies significantly with payload weight, wind condition, and terrain slope. However, existing models simplify or ignore these factors, which often leads to mission interruptions in practice. Moreover, the time window constraints that match rural residents' daily ability are largely overlooked. And second, problem formulation. We instantiate our model on a real-world case study, Zhongyangping village in Zigui Country, Hubei province, China. The scenario includes 1 distribution center and 5 customers nodes, based on real DEM to real data at 30 meters resolution and wind observations from the local meteorological station. The core innovation of our model is a refined allergy consumption framework. Total UAV allergy is decomposed into two components, takeoff and landing allergy, calculated as hover power multiplied by the corresponding time, and cruising allergy, which is a function of distance, payload, wind speed, terror slope, and propulsion efficiency. For time windows, we define two soft delivery windows, morning from 8 o'clock to 12, and after from 2 o'clock to 6, reflecting rural residents' typical daily routines. Delivery outside these windows incur penalty cost. The objective function minimizes total operational cost, which is a sum of allergy cost, earnings penalty, and tardiness penalty. And third, solution algorithm. Because the problem is NP hard, exact algorithms are computationally infeasible for medium and large scale instance. We therefore designed an improved genetic algorithm with 5 key components. Encoding, integer permutation of customer nodes. Each chromosome represents one complete road sequence. Second, cluster-based initialization. Nodes within 1 km are grouped together with 80% probability. Slope exceeding 25 are included in feasible. Third, selection. Roulette wheel selection combined with elitism. The top 5% of individuals are preserved each generation. And fourth, crossover. Cluster segment exchange with 70% probability and random segment crossover with 30% probability. And finally, mutation. Neighborhood swap with 1.5 km with a dynamic mutation rate of 0.1 for generations 1 to 100, decreasing to 0.05 for generation 101 to 200. The algorithm runs with a population of 50, a maximum of 200 generations, and terminate early if improvements fall below 0.1% for 50 consecutive generations. And then results and model comparison. We now present the experimental results. The left panel shows the converge curve of our algorithm, which stably converges within 200 generations from an internal cost of around 65 yuan down to 33.13 yuan. On the right, we compare our proposed model against two benchmarks. Benchmark 1 is a distance-based model that ignores allergy differences, and the benchmark 2 is a simplified payload-based model. Our model achieves an allergy cost of 17.13 yuan, a reduction of 18.2% compared to benchmark 1, and 82% compared to benchmark 2. The additional 16 yuan is a soft time window penalty, which reflects the trade-off between schedule efficiency and delivery compliance. These results demonstrate that our refined allergy model leads to significantly more accurate and cost-effective route plan compared to conventional simplified approaches. And we conducted a sensitive analysis on two practical operational parameters. First, battery capacity at 400 Wh, owning 85.2% of reads are feasible. with an average cost of 38.45 yuan. At 500 WH, the feasible rate reaches 100% with a cost of 33.13 yuan. Increasing capacity further to 600 yields only marginal improvement. Therefore, 500 is a recommended configuration for balancing feasibility and cost. Second, wind speed. As wind increase from 2 to 3 meters per sentence to 4 to 5 meters per sentence, energy consumption rise by 23.4% and the total cost increase by 20.1%. At the highest wind level, 45.2% of roads require replanning. This highlights that wind resistance capacity is a critical design factor for UAVs deployed in mountainous rural areas. To summarize, the paper makes 3 main contributions. We propose a refined UAV energy consumption model that logically accounts for wind speed, terrain slope, and payload, more realistic than existing signal factor models. And we integrate soft time windows aligned with rural residents' routines into the road optimization framework, addressing a gap overlooked in peer literature. And then we design an improved GA with cluster-based initialization and neighborhood mutation, and demonstrate its effectiveness through extensive experiments. Based on our results, we recommend that UAVs for rural logistics be equipped with at least 500 WH batteries, wind resistance capacity of at least 6 meters per sentence, and adopt 4-hour flexible delivery windows. Further work will explore extreme weather conditions, dynamic order management, multi-depot coordination, UAV ground vehicle transshipment, carbon emission, and robust optimization. That concludes my presentation. Thank you very much for your attention. I'm now happy to take any questions.
Thank you for your presentation, dear colleagues. Are there any questions for the speaker?
Thank you for your sharing. May I ask, why did you choose a genetic algorithm instead of other math heuristics, such as simulated annealing or particle swarm optimization? Thank you.
Okay, thank you for your question. Genetic algorithm handles combinatorial routing problems well due to its population-based search, which explores multi-solution simultaneously and avoids local optima. We also incorporated cluster-based initialization and neighborhood mutation tailored to our rural scenario, making GA a nature fit. That said, comparing with other multi-heuristics is a valid direction for future work. Thank you.
Thank you.
Thank you. Any other questions? Then your presentation is finished. Thank you. We will move on to the next presentation, number 3368, game theory analysis or of collaborative regulation in blockchain-based logistic service supply chains. No sound. If you started, we cannot hear you.
Can you hear me now?
Yes, yes.
Oh.
Hello everyone. Today we are excited to present our research titled Game Serial Analysis of Collaborative Regulation in Blockchain-Based Logistics Service Supply Chains. First, let me introduce the research background. The annual scale of China's logistics industry has shown a trend of expanding year by year, with total output value rising accordingly. By the end of 2025, the total revenue of the logistics industry reached 14.3 trillion yuan, representing a year-on-year increase of 4.1%, achieving the goal of rapid development. Several scholars have contributed to the field. Tan et al. Utilized the evolutionary game serial to constructed a three-party evolutionary game model involving state-owned enterprises, operations, audits by audit authorities, and public oversight, analyzing the factors influencing the participants' strategic choices. Focusing on governments, logistics firms, and markets, this paper constructs a trilaterally bonded rationality evolutionary game model under blockchain setting with numerical simulation to analyzing blockchain's behavioral effects on participants and offer suggestions for optimizing supply chain collaborative governance. In my framework, the government takes a leading role by funding the establishment of a blockchain platform and using it for regulatory processes. Logistics enterprises must pay fees to join the platform, and in return, they gain transparency and traceability of products and services. At the same time, the logistics market uses the platform to provide feedback and evaluations on purchased products and services. Based on the framework, we put forward core mathematical assumptions for our game model. For example, if customers in the logistics market express dissatisfaction, the loss incurred by blockchain joining enterprises is L1, while off-chain enterprises incur a loss L2. Considering the positive and negative impacts of government regulation, blockchain adoption by logistics enterprises, and market satisfaction evaluations, we constructed a evolutionary game model involving 8 strategy combinations. According to Freeman's rule, evolutionary stable strategies can be identified by analyzing system stability. By analyzing the partial derivatives to obtain the Jacobian matrix, we calculated the eigenvalues of the 8 per strategy equilibrium points. Theoretical stability results are obtained, then we verify findings through system dynamics numerical simulation, referring to principles from existing literature. Initial parameter settings for the probabilities of behavioral choices by the 3 parties are established at x equals y equals z equals 0.5. First, we analyze the impact of initial strategy variation to analyze the impact of different initial strategic probabilities on the system's evolutionary outcomes. 3 different initial probability levels, low, medium, and high, were set, with other parameters held constant, as shown in figure. Regardless of fluctuations in initial probabilities, the system ultimately converged toward a stable equilibrium. Throughout the evolutionary process toward stability, logistics enterprises consistently respond first by adopting blockchain technology. In reaction, the government subsequently enhances regulatory oversight. However, responses from the logistics market exhibit a lag, since market evolution typically occur after logistics services are completed, resulting in delayed coverages compared to the other two parties. Next, we analyze the utility of the blockchain platform. As the regulatory utility coefficient increases, the time it takes for the government's policy adjustment curve to converge to a steady state shortens from approximately 1.8 years to about 1.3 years. Next, let's turn to logistics enterprises. We examined the impacts of the logistics service value-added coefficients on the probability of logistics enterprises adopting blockchain. When these coefficients varied within a 50% range, the time needed for the system to reach equilibrium declines from 1.5 years to 1 year. Next, we analyze the impact of the quality and safety benefit enhancement coefficients on logistics market satisfaction. Even though the impact of changes in this value on strategy selection is relatively minor, we observe that the time required for the logistics market strategy curve to reach a steady state shortens as the coefficient increases. However, the overall coverage period remains around 4 years, reflecting the inherent lag in obtaining feedback from the logistics markets. We also examined the influence of government support, the preferential tax rates coefficients, and the tax rates on government regulatory efforts and logistics enterprises blockchain adoption. As shown in figure, under strict incentives, due to the substantial fiscal burden of subsidies and tax reductions brought by the government, its enthusiasm for regulation begins to decline after approximately 0.5 years. Interestingly, the strategic adjustment curve of logistics enterprises stability with 0.5 years under this scenario, signifying extremely high enterprises participation. Finally, let me summarize our conclusions. Logistics enterprises are typically the first to adopt blockchain technology. The government subsequently initiates regulatory oversight as standardization becomes necessary. Significant positive correlations exist between improvements in the three core indicators and the speed of evolutionary convergence. Under strong incentive policy characterized by high subsidies and reduced tax rates, the willing of logistics enterprises to adopt blockchain technology rapidly increases. Stability after approximately 0.15 years. That's all for my report. Thank you for your listening. I'm happy to take any question.
Thank you for your presentation, dear colleagues. Are there any questions for the speaker? Please. Yes, please. Your microphone is mute.
Hello, can you hear me?
Yes, we can hear you.
Okay, thank you. Hello, I have a question, and what are the differences between your research and the extant research?
Okay, thank you for your question. Unlike prior research, the research centers on governments, logistics enterprises, and the logistics market as core stakeholders. A tripartite evolutionary game model based on bounded rationality is built to verify via numerical simulation instead of relying merely on theoretical reasoning like most existing works. It quantitatively measures how blockchain shapes participants' decision-making and delivers actionable recommendations to improve collaborative governance across logistics supply chains. Thank you.
Okay, thank you.
Thank you. Any other questions? No? Then your presentation is over. Thank you very much. The next one is number 3369, Economic Benefit Evaluation System of Air Rail Intermodal Logistic Hub and its empirical application, a case study on Hankyu North Station.
Okay. Good morning.
Good morning.
Good morning, respected experts and college. I'm Xiaohua from Wuhan Technology and Business University. Today, my presenter is Economic Benefit Evaluation System of Air Rail Intermodal Logistics Hub and its empirical application, taking Huangshi North Station as research case. My report consists of three parts. Part 1 is evaluation system construction. Part 2 is case empirical analysis based on Huangshi North Station. Part 3 is research, construction, and innovation. We innovated build a Trinity economic benefit evaluation framework with three categories of indicator. First, dynamic financial indicator, FIRR, FNPV, and payback period. Second, static financial indicator, ROI, ROE, BP, and payback periods. Third, debt service indicator, debt repayment period, and interest coverage ratio. This multi-indexed from complete systematic evaluator system. Now let's move into the empirical part focused on Huangshi North Station Aerial Express Exploration Project. The project covers 11,000 kilometers in store HGV and automatic strong equipment. With design annual logistics throughput of 13 million pieces. Total investment is 60 million RMB, and the whole project cycle is 11 years. In technicals, investment according for 12.3% of total cost to realize smart logistics upgrade. Here are dynamic financial and debt indicator after tax. FIR is 22.06%. FNPV reaches 18.39 million yuan. Payback period is 5.72 years. In terms of the capacity, debt repayment period is 5.63 years, and ICR is over 2. Reflecting sound debt paying ability. For standard indicator, the project's ROI is 25.27% and ROE is 96.3%. 9%, represent excellent investment of profitability. We complete sensitive and break-even analysis for risk assessment if remained false by 15%, if IRR remains 16.98%. Besides, the project only needs 46.16% capacity utilized to reach break-even point, showing strong anti-risk capacity. Three key closing. First, our Trinity evaluation system can accurately evaluate aerial intermodal have economic benefits. Second, Huang's North Station project has high profit, strong risk resistance, and good survival. Third, the system is practical to decision making of similar projects. Three, research involved customizing exclusive evaluation system, combination of international logistic trend, specific real race ampere verification. That's all of my present. Thank you.
Thank you for your presentation. Dear colleagues, any questions, please? I can see one.
I have one question.
Yes, sure.
Thanks for the presentation. And my question is, what primary indicators from your economic benefit evaluation system and you built for the aerial intermodal constructed in your paper? And what is the evaluation focus of each category?
Okay, thank you. The evaluation system consists of three first-level indicators: dynamic financial indicator, static financial indicator, and surveillance indication. Dynamic financial indicator include financial internet rate of return, financial net present value of investment payback period, which evaluate the time value of the caption, project profitability, and the recovery speed of investment. Stat financial indicator cover return on total investment, return on equity, break-even point, and operating income growth rate, measuring returns per unit investment, shareholder gain, project risk, and long-term development potential. Several indicators contain no repayment period and interest coverage retail, assessing the project's capability to repay debts to and cover interest expansion. Thank you.
Thanks for the answer.
Thank you. Any other questions? No? Then your presentation is finished. So the next one is 3374, Financial Risk Management of Supply Chain Resource Integration in Semiconductor Industry, method based on the Z-score model and F-score model.
Hello, everyone. Good morning. Is the PPT show okay?
Yes, we can see your screen, please.
Okay. The sound is larger. Okay. Okay. My presentation this morning, the title is Financial Risk Management of Supply Chain Resource Integration in Semiconductor Industry, Methods based on Z-score model and F-score model. My name is Wu Zhaozhe, and the whole structure of the presentation is in 5 parts. Part 1, Introduction, with the comprehensive development of science and technology and the continuous progress of intelligent facilities. Semiconductor technology is increasingly being applied, and the demand for its equipment is constantly increasing. Actively integrating various technological resources and achieving integrated development of industries in supply chain has become a clear trend. An effective way to address various challenges in the development of the semiconductor industry is to achieve mergers and acquisitions of enterprises. The financial risk is the process of supply chain resource integration is an important research area. The domestic literature generally agrees that financial risks in mergers and acquisitions run through the entire process. The identification methods of financial risks mainly rely on financial indicators, DuPont analysis system, and other methods. Some foreign literature mainly uses cost analysis methods to discuss sustainable supply chain systems, while others apply big data linking to the entire supply chain management to form effective integration of the supply chain. This study uses the Z-score model and F-score model methods to identify overall financial risks, with the aim of making the identification and control of financial risks more complete. Part 2, Methods and Processes for Identifying Financial Risks. Figure 1 is the process of using Z-score and F-score to identify financial risks. The Z-score model is an early warning model based on relevant financial data of listed companies to identify risks, providing intuitive risk references for acquirers and helping to determine whether the company is facing financial difficulties after the merger. The F-score model considers the impact of cash flow factors on corporate financial risk based on the Z-score risk model, and determines whether a company has bankruptcy risk, resulting in higher prediction accuracy. Part 3, Case analysis of financial risk of the M&A between two semiconductor companies. 3.1, Background and motivation analysis of an M&A transaction. Company JCET specializes in providing domestic integrated circuit packaging and testing services with a wide range of product applications and high attention to scientific research. It not only has advanced production facilities and equipment, but also has a high degree of completeness in the industrial chain and can independently complete chip packaging and the final product testing work. Company SDS has an excellent R&D team and advanced technology, mainly engaged in the research and development, packaging, and testing of flash storage products. Its core products have been deeply applied in various consumer electronics, such as communication, automobiles, and smart homes. After the M&A activities, the resources of the two companies can be deeply integrated, further breaking through the limitations of technology and promoting the sustained and stable development. The two companies have a collaborative relationship between upstream and downstream. JCET needs to purchase raw materials from upstream chip companies, while company SDS needs to conduct packaging testing after developing products. After the merger and acquisition of the two companies, they can integrate limited market resources and enhance market
competitiveness. 3.2 Risk identification of JCET's acquisition of SDS. After the merger of the two companies, the name of the company remains JCET. Table 1 shows the formula of index X. Table 2 presents the Z-score of JCET has decreased from 3.9026 in 2022 to 2.7908 in 2023, showing a significant downward trend overall. However, the Z-score in 2024 is below 2.9, indicating a gradual increase in financial risk. Through specific analysis, it is found that the X3, X4, X5 indicators have a significant impact on this score, leading to a decrease in it. From 2022 to 2024, there has been a significant decline in the X3 index, with net profit decreasing year by year, indicating a significant weakening of the company's profitability. The X4 value has also shown a significant decrease compared to previous years, which is related to the company's acquisition of SDS. During this stage, the X5 indicator also decreased. In 2022, it also originally at a high level, but by 2024, it has dropped to a low level. This also reflects a decrease in the proportion of the company's comprehensive marketing revenue in total assets. If the future business and debt situation of the enterprise cannot be improved, it will face huge financial risks. Table 3 shows the values of various variables in the F-score model. From the formula calculation results, it can be concluded that the calculation methods for the first, second, and fourth indicators of the F-score model are completely consistent with those of the Z-score model, but there are differences in the calculation methods for X3 and X5. The numerator of X3 is the sum of net profit and depreciation, and the denominator is the average total liabilities, while the numerator of X5 is the sum of net profit, depreciation, and interest, with the denominator unchanged. The critical value of the F-score model is 0.0274. When company's F-score is lower than 0.0274, it indicates a higher risk of bankruptcy, and vice versa, it indicates that the company is less likely to go bankrupt. Combining the Z-score risk model and F-score risk model analysis, it can be concluded that there is a certain overall financial risk after the acquisition. Part 4. Financial risk control measures for JCET's acquisition of SDS. And control overall financial risk. By regularly calculating the Z-score and F-score, the financial risk level of the enterprise is dynamically monitored, and timely warnings are issued when the values deviate from the safe range. At the same time, JCET should establish a sound risk warning mechanism and plan R&D investment and market strategies in advance. In addition, JCET should improve its financial supervision to ensure the authenticity and accuracy of financial data, guarantee the effectiveness of Z-score and F-score model evaluations, convey robust financial signals to investors, and enhance market confidence. The second measure is reduce pricing risk. Pricing risks mostly occur before mergers and acquisitions. JCET should comprehensively use multiple methods for valuation and accurately measure the value by referring to the industry level. It can also set performance gambling on post-delivery adjustment clauses in the agreement. In addition, JCET should pay attention to comprehensive due diligence and can help third-party professional institutions to ensure the scientific and reasonable pricing of mergers and acquisition. The third measure is control financing payment risks. Enterprises should optimize their capital structure and financing channels and actively explore innovative financing models such as supply chain finance and asset securitization. At the same time, adjust the ratio of self-owned funds to external financing reasonably. Dynamically optimize the financing structure and reduce capital costs and financial risks. For exchange rate risks, on the one hand, JCET can use forward contracts to lock in the upcoming US dollar payment exchange rate and hedge against the risk of RMB depreciation. On the other hand, JCET can also optimize the company's own settlement currency structure by increasing the holding ratio of US dollar income or assets within the scope of business. Part 5 Conclusion. The first is corporate financial situation. The impact of mergers and acquisition is significant, and overall financial risks are on the rise. At the same time, the decrease in net profit during the initial integration period after mergers and acquisitions will weaken the profitability of the enterprise. The second, cash flow introduction. After the introduction of the F-score model with cash flow factors, the limitations of the single Z-score model were effectively compensated for, and more comprehensive risk warnings were provided. The comprehensive application of the two models confirms that considering cash flow can more comprehensively evaluate the actual financial risks after mergers and acquisitions. Guidance for industry enterprises. This study validates the effectiveness of the multivariate financial risk warning model in the evaluation of mergers and acquisitions in the semiconductor industry and provides feasible risk response plans. Other electronic equipment manufacturing enterprises in China can also obtain a data-driven risk identification perspective and management reference from this study when integrating supply chain resources and conducting mergers and acquisition activities. That's all. Thank you.
Thank you for your presentation.
Thank you.
Dear colleagues,
I would
your
like
question,
to
please.
ask a question.
Okay, thank you.
Why use F-score to evaluate financial risk after using Z-score model?
Because it's a question. Because F-score model introduces the cash flow factors and it's a effective compensation for the whole financial risk evaluation. So the comprehensive application of the two models confirms that considering cash flow can more comprehensively evaluate the actual financial risks after mergers and acquisitions. Thank you.
Thank you. Any other questions? No. Thank you for your presentation. We are moving to the next one.
Okay.
The next presentation number 3388, construction of an evaluation system for the coordinated development of port industry city in Inland River, port economic zones of Henan province.
Okay. Good morning, everyone.
Good morning.
I will present my paper, How to Build an Evolution System for Port Industry City Coordination in Henan's inland river areas. Inland shipping is green and low cost, but here in Henan we face a struggle problem, strong road and railway, weak water transport. Ports are small and scattered, industry near ports are underdeveloped. The good news is that new policies are in place. The Henan Port Industry Plan is pushing for major upgrades. Zhoukou Port is now a national logistic hub, and Xinyang Port is growing fast. So the question is, how can port, industry, and cities grow together? Most existing studies focus on coastal ports or sea-river combined ports. They overlook the fact that central inland ports are different. Smaller scale, low channel grids, and bulk-dominate cargo. Our goal is to build a practical evolution framework tailored for Henan's inland ports. We want to give planners both theoretical support and actionable tools. Henan's shipping mainly use the Shanyin River and Huai River. We see one main, three auxiliary pattern. Industries are dominated by traditional bulk goods like grain and coal. High-tech industry are rare. City support is uneven. The key numbers are shown at the bottom of this slide. How do the three systems interact? We found a closed-loop mechanism. Ports lower logistic costs and improve transport links. This attacks industry and expands cities. Industries created demand for better port facilities and push city service to upgrade. Cities build infrastructure, bring in talent, and make policies. They support both ports and industries. So the three parts reinforce each other in a circle, leading to mutual upgrading and high-quality development. Based on this mechanism, we built a four-dimension system with 16 indicators: port development, industry development, urban support, high quality. This covers the ports, the factories, the city, and green growth. We use entropy weight mass to set indicator weights. It's purely data-driven, so there is no human bias. Then we use topses to rank performance. It compares each port against the best and worst cases. The final score tells us how well each port is doing overall. Why this combination is objective, fair, and easy to compare across different regions. To measure how well the three systems work together, we use the coupling correlation degree model. It shows both the interaction stress and the overall synergy level among ports, industry, and city. We set the port as core-driven, with industry and city as supporting rules. The results are divided into 5 levels, from extreme disorder to high correlation. We also use an obstacle degree model to pinpoint exactly which indicators are the real bottlenecks holding back progress. We suggest 4 clear strategies. First, stronger ports, upgrade the main waterways, add bigger berths, and introduce smart technology. Second, better industry, build a port plus industry chain for logistic to processing. Push smart manufacturing and let each city find its own industry role. Third, improve cities, invest in road and public facilities, connect port zone to city centers, improve talent policies and the business environment. Fourth, higher quality, build green waterway and ecologic ports, deepen cooperation with coastal ports, improve right water and raw water links. In summary, Henan's inland port economy is at a stage of small scale, weak base, but big potential under new policies. Our 16 indicators four-part system combines three models to precisely identify weak spots. The key are stronger ports, better industry, improved cities, and higher quality. This framework is useful not only for Henan, but also for other inland provinces facing similar challenges. My speech is over. Thank you for your attention.
Thank you for your presentation, dear colleagues. Are there any questions? Yes, please. Young Fan.
Have you already applied this evaluation system to any specific port in Henan? Could you share any preliminary findings?
Okay, yes, thank you for your question. This paper builds the framework. We are now collecting data for Zhoukou and Xinyang. Early look show that Zhoukou has decent port facility, but weak industry clustering and few high-tech firms. Xinyang is growing fast in cargo volume, but city support like roads and keeping talent still lacks. Full results will come in our next paper. Thank you.
Thank you. Any other questions? No, thank you. Your presentation is over. The next one, number 3467, optimization of cold chain logistic routing with time-dependent windows and energy consumption based on hybrid genetic algorithm.
Can you hear me?
Yes,
Let's share my screen.
sure.
Can everyone see my screen?
Yes.
Yes. Okay. Let's get started. Good morning, distinguished professors, fellow scholars, and guests. My name is Yu Yaxing, and today I'm honored to present our research titled Optimization of Cold Chain Logistic Routing with Time-Dependent Windows and Energy Consumption based on Hybrid Genetic Algorithm. Today, we will discuss a pressing issue at the intersection model logistics and environmental sustainability, and present a mathematical and algorithmic solution to address it. Okay, my presentation is divided into three main parts. Part 1 covers the introduction, Part 2 detail the mathematical model and algorithmic framework, and Part 3 presents the numerical experiments and conclusion. Now let's begin with Part 1. Looking at the background and motivation, as you know, the global fresh food market is booming. Currently, the refrigerated transport sector accounts for roughly 15% of global fossil fuel consumption. It's a major source of greenhouse gas emissions, and many traditional routine models often overlook how ambient temperature impacts cooling energy, leading to massive waste. In real-world operations, cold chain logistics face a dual challenge. First, urban congestion changes traffic speeds throughout the day, and delaying deliveries. Second, extreme heat wave due to global warming significantly increase the cooling loads. The real problem is their compounding effects. If a truck is stuck in the traffic jam during the peak afternoon heat, the energy drain increase exponentially. Therefore, our study has three main objectives. First, to build a refined energy mode that integrates dynamic traffic data with real-world urban temperature gradients. Second, to develop an ICAILE2026 framework to solve this NP-hard problem. And third, to validate the model's economic viability and thermal resilience under extreme global warming scenarios. To achieve these goals, we formulated a comprehensive objective function. As you can see, our goal is to minimize the total cost, which consists of three main parts. First is transportation cost. It quantifies standard fuel expenditure based on physical distance. Second is the energy cost. This evaluates the cooling energy required, factoring in the ambient temperature and any travel delays caused by congestion. Finally, a penalty cost acts as a soft constraint, balancing energy saving against the economic loss of missing customer time windows. And because this problem is NP-hard, exact solver struggle, we designed an integrated algorithmic framework. We use a standard genetic algorithm for broad global exploration across the solution space. However, GA can easily get trapped in local optimal, so we combined it with adaptive large neighborhood search for local exploration. Now let's look closer. It's released on targeted removal and repair. The worst cause operator identifies and extracts nodes that cause massive heat load. The time-oriented operator removals nodes caused in peak hour traffic. Once these inefficient nodes are extracted, our greedy repair strategy intelligently reinserts them into new positions within the route. It allows chooses the position that minimize the increase in the objective function. Now for our numerical experiment, we use modified Solomon benchmark in instances over 12-hour daytime operational window to simulate real-world dynamics. We applied a 40% space reduction during morning and evening rush hour. We also incorporated real summer climate data from Wuhan. The temperature starts at 29 degrees Celsius and reaches a peak of 38 degrees Celsius at 3 p.m. Now let's move to the results. This convergence chart shows that the light blue dash line represents the standard genetic algorithm, and the orange dotted line represents the tab search. As you can see, both standard algorithms experience the premature convergence. They got trapped in local optimal around the fifth generation and flattened out. However, look at the solid green curve representing our proposed hybrid approach. Thanks to the ALNS mechanism kick in, it successfully escaped this trap. It continued to dive deeper, find better solution with low energy consumption in later generation. Ultimately, our hybrid method achieves a 12.4% average cost reduction. And we also visualize the improvement spatially. This slide compares the actual delivery routes. On the left, the traditional distance, first route dispatch a truck into the congestion city center at 8:30 a.m. It gets stuck in severe traffic, wasting immense cooling energy. On the right, our optimized route dynamically alter the sequence. It arrives at the city center at 11:15 a.m. when traffic is smooth. This strategy, spatial temporal shifts successfully, avoid both congestion and peak heat. And finally, we test our model's thermal resilience, which happens when the peak temperature rises from 25 degrees Celsius to 40 degrees Celsius. As the bar chart shows, our cost saving margin actually increases as the environment gets hotter. At an extreme heat of 40 degrees Celsius, the HGA achieves an 16% cost saving. It maintains its economic viability because the algorithm automatically learns to reschedule more deliveries to cooler early morning hours. In conclusion, our framework effectively reduced the logistic cost by average 12.4%. That's bring me to the end of my presentation. Thank you for your attention. Now I would be happy to answer any question.
Thank you for your presentation, dear colleagues. Are there any questions for the speaker? Yes, please.
Yes. Thank you for your sharing, and I have a question to ask. How does your algorithm avoid missing strict customer delivery times when it tries to shift deliveries to cooler parts of the day?
Thank you for asking. This is a reasonable concern. The algorithm balances very carefully, where it naturally wants to move deliveries to cooler hours to save energy. Missing a customer times window creates a heavy penalty cost in our math model. If a schedule change makes a delivery too late, the total cost goes up, and the algorithm will reject that route. So it only shifts deliveries to cooler hours if the customer time window allows it, or if the energy savings are so huge that they overweight a very tiny delay penalty. So I hope I answer your question.
Thank you.
Thank you for asking.
Thank you. Any other questions? No. So thank you for your presentation. The next one is number 3404, Network Evaluation Mechanism of Intelligence Logistics Supply Chain Ecosystem. Three, 404.
Okay, thank you. Can you hear me?
Yes.
Okay. Hello, good morning. My name is Chen Yichao, and my conference paper name is Network Evolution Mechanism of Intelligence Logistic Supply Chain Ecosystem. I will present my paper from this four parts. The first part is the logistic supply chain ecosystem network. And first, I deny this network as ecological environment of supply and demand networks formed on the chain by supply chain enterprise consumers and intelligently driven digital platform and other stockholders. And this network also has stability characteristics through the flows and integrated of intelligent logistic price. All network entities establish interconnect and interdependent related relationships. And the second part is the logistic supply chain economic network dynamic mechanism. And the first part is the network in internal dynamic mechanism, and it's including the synergistic efficiency-driven mechanism. This mechanism is about to create a effect where 1 + 1 is bigger than 2, with all particles entities deriving greater benefit than they would individually. And the second is the customer demand pooling mechanism. The third is intelligent touch knowledge and empowerment mechanism. The other mechanism is the network external dynamic mechanism. It's about including the policy guidance mechanism and legal support mechanism, especially the legal support. It's about solution paths, the legal regulation must be embraced to ensure the orderly conduct of online legislation. The third part is the logistic supply chain ecosystem network evolution mechanism. This mechanism is about the interaction mechanism between the enterprise and customers. The following is about the relevant ecos. And the second interaction mechanism is about enterprise and intelligent platforms. And according to the about the conduct, I made the simulation result analysis. It's about the network density, and the simulation one is for fixed scale. There are no policy related factors, and the simulation two is about the fixed scale involved policy factors. And the evolution insight is about each collaborating unit select property partners based on its specific needs relating the dynamic evolution characteristics. And the final part is about my conclusion. I think this network is about the internal and external driver touch knowledge and mechanisms reshape the ecosystems. There also has two contributions. The first contribution is theoretical. This study is bridges supply chain management, ecosystem theory, and network science. The second contribution is about the practical insights. It's valuable for enterprise strategy, platform government, and policy formulation to build the logistic economic ecosystems. Okay, thank you. That's all.
Thank you for your presentation, dear colleagues. Any questions? Yes, please.
Good morning. I have a question. What are the components of logistics supply chain ecosystem network evolution mechanism? Thank you.
Okay, thank you for the questions. I think I think about the evolution mechanism, and there also has consist of internal and external mechanisms, including the policy guidance, the legal support, and intelligent touch empowerment. Also has some synergistic effect drive the mechanism. That's all. Thank you.
Thank you. Any other questions? No, thank you for your presentation. It is over. The next one is number 3465. Analysis and evaluation of key mineral supply chain resilience based on entropy weight, TOPSIS. Three, 4, 6, 5. Cannot find. There is no speaker, yeah? For 3, 4, 6, 5. Okay, let's go to the next one. Presentation number 3425. Reform and practice. AI-driven 5-step for linkage teaching model in international logistics. 3425. I can see it. Are you ready? Presenter of 3425. Chen Fenjian, probably. No?
I see that the author is here.
Yeah, I can see, but
Yeah.
no answer.
Xin Li. Yes. Wait a minute.
Okay.
Okay, dear professor. Sorry.
No problem.
Okay. Okay, today I will introduce our curriculum reform on international logistics from 6 dimensions: background, ancients, existing problems, 3-dimensional reform strategy, teaching implementation, and practical outcomes and achievement promotion. International logistics is an optional course for our top-up undergraduates with 2 credits and 32 class hours, delivered in small group teaching of less than 30 students, closely linked with Belt and Road Initiative and supply chain security strategy. The curriculum highlights cutting-edge sectors, including China European railway experience and green logistics and cross-border cold chain. With 16 authentic enterprise-run projects running through teaching contents, we launched a questionnaire several and collated 272 valued samples at a 90% recovery rate. Most students prefer project-based learning and actively utilize online resource with decent communication skills. However, nearly 90% of students mostly interested in tedious theoretical knowledge, and over 92% struggle to apply fragmented knowledge into real practice due to inadequate software proficiency, which directly pushes us to carry out targeted curriculum reform. Okay, and sorry. Okay, and the core division of traditional teaching lies in poor alignment between course content and local enterprises' practical demands, leading to their drawbacks. First, the obvious gap between zeros and on-site operations entities, graduates workplace adaptation cycle. Second, excessive scattered content trigger students' cognitive overload and low learning efficiency. Third, isolated knowledge fails from a completed system, restricting knowledge transformation and weakening industry education cooperation. To solve these challenges, we adopt school enterprise cooperative education and design a unique three-dimensional integrated teaching framework. Okay. The first dimension focus on content reconstruction, shifting from knowledge cramming to competency cultivation. We divide the work course into 6 modules covering trade roles, multimodal transport, and smart warehousing, and building real case of overseas warehouses and cross-border grassy logistics to improve students' global problem solving ability. And then the second dimension in modular reorganization guided by enterprise leaders where industrial projects are implemented into corresponding modules to realize full project-oriented teaching. The third dimension builds multi-part cooperation mechanism, including joint and development and dual teacher co-teaching, supported by virtual simulation technology. We connect classroom assessments with real corporate business. Okay. And the second, and the next, we design a standard 5-step teaching process for every project class. Enterprise matters. First, share real industry pain points. Students then combine practical troubles with core knowledge and design important plans based on Wuhan's local and cold chain industry. After scheme deduction, students optimize proposals on 百叠那个 simulation platform under dual teachers instruction, and mutual solution will be adapted by cooperating firms or transformed in school research topics. Okay. Meanwhile, we replace single final exam with multi-desk assessment, group present 30%, competition performance 10%, simulation practice 20%, individual performance 20%, and online tests 20%. Combine evaluation from students, instructors, and enterprise choice. Remarkable results have been achieved after reform. Students' satisfaction surpasses 93%, and many students win national logistics contest awards and secure job in future global 500 corporations with high employer recognition. And final, our reform model and teaching kits have been applied in peer courses inside our university and promoted to related majors of other colleges. In the future, we will update teaching content to keep pace with the industry upgrades. Okay, thank you all for listening.
Thank you for your presentation, dear colleagues. Are there any questions for the speaker? Yes, please. Yes, you can ask.
From the perspective of industry education integration, what's the basis for weight allocation of multidimensional whole process assessment system after implementing the three-dimensional integrated teacher reform for the international logistics course?
Okay, thank you. Thank you for your question. The weight setting is based on the three core training objectives of knowledge and ability and comprehensive quality of the course, combined with the importance of each teaching link and practical training content. Group collaboration accounts for the largest preparation as project learning is core. Virtual simulation, individual performance, and online tests match daily learning. Competition performance is set at a lower weight as an optional ability improvement indicator. Okay.
Okay, thank you.
Thank you. Any other questions? No, that your presentation is over. The next one, presentation number 3428, Knowledge Enhanced Small Language Models for AI-enabled decision support in delivery delay prediction for smart supply chains.
Okay, can you hear me?
Yes.
Okay, thank you. Okay, dear expert and research, I'm Jingling Wang from the Guangzhou City University of Technology. Today, I'm very delighted our research about knowledge enhanced small language model for the AI-enabled decision support in delivery delay prediction for smart supply chains. Okay. This is 5 part. Okay, in the first, let's look at the research background. In the model, logistic delivery delays can cause chain reaction risk. Enterprise has raised fund to hand against risk, but for small and medium size enterprise, in the supply chains, a series delay can be fatal. So that's the core need of small supply chains has changed from handling problem afterwards to taking proactive action beforehand. However, exciting research have a clean limitation. Most student focus having on accuracy, but in real life business, the cost of maintaining a high risk or orders is high. Moreover, traditional model are black box. If we just give business start a probability number, they have no idea why it happened and find ways to the risk also need more time. Okay, under 3 parts in the exciting in research. First, using the model like XGBoost or LSTM and so on to make prediction as accurate as possible. But the key issue is weak interpretability. Second, using the metaphor like shape based on the prediction model uh, to enhance the explanations, but the business start face cognitive limitation because it's just a number. Although a third using large language model, although they can output the natural language for the declared, but the cost is too high, and there's no stabilization vertical model for delay prediction. To therefore, to address the gap above, we propose knowledge-enhanced small language model. This is our model framework. We no longer split prediction the explanation into two deep. Instead, we combine them into one. Now let's look at the model detail. First is semantic transformation. We serialize structural order data into natural language and embed statistical information like historical degree rate. This brings the gap between the table and the language. Second, knowledge enhance the representation. And beyond base tasks, we integrate machine learning prediction probability on the training site and business statistical rules as extra features into the task, making inference more robust. Third, is about the reasoning distillation. We use the large model to generate reasons deep as a teacher and distill this ability into a small model. That the small model can both predict and expand. Finally, do the output have a double kernel? The model output both declare probability for the decision making and the natural language for explanation for the reason. We have a compare traditional trace model and language model on a reliable workspace trans data site. Although trace model like XGBoost it's the overall accuracy and IOC the first, but our models had more scientific record in a radical signation of and the loss of missing a high race orders is in numbers, so high recall has more practical business value. At the same time, we had more a balanced study also provide that once the teacher's model transfer of source about such as COT is removed, the FE score declines 7. So there is necessary of injecting reasoning knowledge from the large model. For different order, our model can directly output the human readable action cues. For example, the high risk orders, it will clearly point out that is due to a long transportation distance or high historical delay in the Curry transform model. The model transform data future into action can helpful in scientific decision support. The last is a conclusion. It's that this study makes three major contributions. First, in theory, is promote the application shift from the pursuing accuracy to pursue decision effective. Second, in methodology, it cleanly combines structural table data with the semantic reasoning of language model. Third, in application, explore a low computing cost, high output intelligent transformation plan for research constrain the SMES. Of course, this study currently limit to a single open source data. In the future, we will explore course in industry variation and plan to enhance more data. Thank you for your listening.
Thank you for your presentation. Dear colleagues, are there any questions for the presenter? Yes, please.
Good morning. I have a question. In the proposed framework, the teacher model generates reasoning traces for destination. Why can't they enable a much smaller student model to learn risk explanation? Thank you.
Okay, thank you for your question. The reasoning trains can be viewed as a struggle travel through with a three main step. Identify key risk factors, modeling causal relationship of the risk, and providing actionable recommendation. During destination, we apply ORA for parameter effective fine-tuning, allow the student model to learn from this reasoning task and capture the teacher's model reasoning logics, rather than just predictions. Our evaluation results show that removing reasoning traits lead to the significant drop in FE score, so it is important. Thank you for your question.
Thank you. Any other question? No, your presentation is over. The next
Okay,
one.
thank you.
Yeah. The number is 3432. Green trade barriers and the carbon cost transmission mechanism in cross-border supply chains. A quantitative measurement study. 3432.
Good morning, everyone. I am Wu Xiaofeng from Hubei University of Technology. Good morning. Good morning, everyone. I am Wu Xiaofeng from Hubei University of Technology, Engineering, and Technology College. Today, I will present our research on green trade barriers and carbon cost transmission in cross-border supply chains, with a specific focus on the EU's carbon border adjustment mechanism. Per Kenyan own as a CBM, our study answers one key question. How do carbon costs flow from a Chinese factory to an EU customer? And how can we measure this process? Part 1 is the background and research gap. Let me start with the background.
The other. Maybe you open too much software. So open only one, close the others. Echo, too big of the echo. 我用中文告诉你，你打开太多的了，所以有回声。你只打开一个你宣讲的这个报告。Clear? Sorry for disturbing you.
Okay, yes.
It's okay now.
It's okay now.
Too big, the
Too
echo.
big, the echo.
Disappeared. Can you hear us?
Let me start with the background. From 2026, the EU CBM will impose carbon tariffs on imported steel, aluminum, cement, and other high-carbon products. For Chinese exporters, this means a significant cost increase. For example, steel carbon costs will rise by about 650-690 RMB per ton, reducing price competitiveness by 15-20%. In 2023, China exported 152 billion euros of steel and 48 billion euros of aluminum to the EU. These industries have long, complex cross-border supply chains. So understanding how carbon costs transmit through these chains is critical. However, traditional research focuses on static production or logistics costs. It does not capture the dynamic cross-border nature of carbon cost transmission. There is no clear analytical framework or quantitative model for this problem. That is the gap our study fills. We built our work on three theoretical foundations. First, global value chain theory, which tells us that costs flow through connected nodes across countries, and the bargaining power determines who pays. Second, system dynamics theory, which helps us model complex, non-linear feedback loops, such as how carbon prices affect technology investment, and how technology then reduces future emissions. Third, cost transmission theory, which explains how cost shocks propagate upstream and downstream through price mechanisms. These theories together give us a strong foundation. Now, let me introduce our quantitative measurement model. We designed a three-stage model. Stage one policy shock. We calculate the initial carbon cost using CBM carbon price product embedded emissions. Stage two, stage by stage transmission. We track carbon cost as it moves through production, logistics, and customs clearance. At each stage, we consider cost superposition, adding new costs, and attenuation loss due to friction. Stage three, industry adjustment. We apply two adjustment coefficients. One for carbon intensity, one for industry concentration. High carbon, low concentration industries get a larger application factor. We define several key indicators. E equals product embedded carbon emissions, 10C, or per ton of product. P equals CBM carbon, price MV 10C, or beta equals transmission attenuation coefficient, 0 to 1 gamma equals industry adjustment coefficient, 0.8 to 1.5. The core formula for final carbon cost per unit is ICCU equals CI 1 beta plus CCR plus CH gamma M, where C is initial cost, CCL is logistics cost, CH is clearance cost, and M is quantity. This model is dynamic and can adapt to changes in carbon prices or policy rules. We apply the model to Chinese steel and aluminum exports to the EU. Here are the key results shown in Table 2. Aluminum carbon cost is 10,450 RMB per ton, which is 7.2 times that of steel. Why? Because aluminum's carbon intensity is 12 tons or per ton, while steel is only 1.8 tons. So initial carbon cost for aluminum is much larger. In terms of cost structure, initial production cost accounts for about 68% of total carbon cost. Logistics and customs clearance together account for 20-30%. Transmission efficiency is high, so 80% of the initial carbon cost is passed downstream. This is because steel and aluminum exporters have strong bargaining power and improving supply chain coordination. Our sensitivity analysis shows that carbon price and industry carbon intensity are the most influential factors. A 20% increase in carbon price leads to a 20% increase in final carbon cost. The attenuation coefficient has a smaller effect. Based on our findings, we propose 4 Fs. Align carbon accounting with ISO 14067 and CBM rules. Improve coordination among supply chain nodes. Share information. Optimize routes. Reduce nodes. Invest in low carbon technology, hydrogen steel making, low carbon aluminum, CCS. Strengthen policy support, mutual recognition of carbon markets. Subsidy funds. Industry training. In conclusion, our model provides a practical tool for exporters to anticipate carbon cost shocks and optimize supply chain strategies. Carbon costs are not just a production issue. They propagate through logistics and clearance. Managing them requires a whole supply chain perspective. Thank you. I am happy to take questions.
Thank you for your presentation. Any questions, please?
I have a question. Your model use a fixed attenuation coefficient of the 0.2. How much does the result change if this coefficient is different? Thank you.
That is a great question. Let me explain. In our sensitivity analysis, when we change beta by plus or minus 20%, the steel carbon cost changes from about 445 RMB item to either 1,612 or 1,277 RMB item. That is about an 11-12% change. So beta does affect the result, but less than carbon price or industry carbon intensity. In the future, we can estimate industry-specific beta values using real logistics data. Thank you.
Thank you. Any other questions? No. Your presentation is over. Let's move on to the next one. The next one is number 3438. A calculation model for freight volume of individual branch channels in multi-branch graded estuarine waterways based on AIS data.
Thank you. Can you hear me?
Yes.
Thank you. Hello, everyone. My name is Tianhang Gao, and I am representing the authors of this paper. Today, I will present our research on freight volume calculation for individual branch channels in multi-branch graded estuarine waterways. This work was conducted at the Transport Planning and Research Institute. First, let's understand the context. Estuaries where rivers meet the sea are dynamic environments where multiple channels or branches often form. In China, significant investments have been made to upgrade these waterways to support the growing demand for river-sea transportation. However, a fundamental question remains: how much cargo actually passes through each individual branch? This information is vital for making informed decisions about future infrastructure investments and ensuring efficient management of these complex waterway systems. The core problem we address is the balance of reliable data and methodologies for calculating freight volume on each specific branch. Existing approaches typically provide an overall figure for the entire estuary, which is insufficient for detailed planning. For instance, simply assuming ships always take the shortest path overlooks crucial constraints such as water depth, which dictates which ships can use which channels. This oversight results in estimations of the actual cargo flow distribution among the branches. To overcome these challenges, we propose a normal two-step method. First, we calculate the total freight volume passing through the entire estuary system by combining two powerful data sources: AIS data, which tracks vessel movements, and maritime visa records, which document cargo details for port costs. Once we have the total volume, our second step is to allocate this volume to each individual branch. We do this by analyzing AIS data to count the number and the type of ships using each branch, and then calculate a specific average loading rate for these ships within that branch. Multiplying this together gives us the freight volume for each channel. For step 1, we identify vessels passing through key inland ports. For inbound ships, we records through unloading cargo, that's upstream volume. For outbound ships, loading cargo gives downstream volume. We cross-check with official port data to ensure accuracy, producing a robust total freight volume. Step 2, allocate volume to each branch using AIS data at cross sections on each branch. We count ships by type and size. Then we use the least squares method to calculate the average loading rate per ship type per branch. Finally, we multiply ship count, carrying capacity, and the loading rate to get a freight volume for that channel. We applied our method to one case, a two-branch estuary in China, as shown in this diagram. After proposing the AIS and visa data for various ship types, we obtained the following results. Branch A carries an estimated 1.15 billion tons of freight, while Branch B carries about 283 million tons. This clear differentiation demonstrates the method's ability to quantify the use of each individual channel. In conclusion, our study presents a scientifically valid and practical applicable method for calculating freight volume on individual branch of multi-branch estuaries. By integrating AIS and maritime visa data, we have successfully addressed a critical data gap. The results are not just theoretical, they provide actionable information for policymakers and engineers to plan future waterway improvements and manage existing resources more efficiently. Thank you for your attention.
Thank you for your presentation. Any questions for the presenter?
Hello, good morning, everyone.
Yes.
Your research presents a novel and integrated method for very practical problem. However, all models have their limitations. What do you see as the main limitation of your current methodology, and how do you envision it being improved in future research?
Thank you for your question. The primary limitation of our method is its dependency on data quality. The accuracy of our estimation is directly tied to AIS signal coverage and the precision of visa records. For smaller ships, vessels, or certain regionals, AIS data may be sparse, introducing positional errors. Another limitation is that our average loading rate calculation, while an improvement relies on a statistical fitting approach that may be fully capture and the complexity of real-world ship operations. For future improvements, we plan to integrate more diverse data sources, such as real-time hydrological and weather data, and explore machine learning techniques to better predict loading rates and route choices. Thank you.
Thank you. Any other questions? No. Thank you for your presentation. It is over. And we have the next one. The next one is 3442, which is the moderating role of social norms in the relationship between environmental attitude and e-commerce return intention, a scenario experiment.
Good morning, esteemed professor and colleagues. Today, I will present my research on the demolding role of social norm in the relationship between environmental attitude and e-commerce return intention, a scenario experiment. We all familiar with the dual couple goals. However, there is a hidden contradiction in the digital economy where we promote green consumption. The convenience of e-commerce has attracted a return epidemic. Let me put this into perspective. By 2025, the return rate in live streaming e-commerce hit 35% to 45%. During Double 11, it urged to 61.5%. For fast fashion, exceeds 8% pedally. Return creates a dual resource consumption. The forward delivery plus the reverse logistics. This generates double packing waste and carbon emissions. It's a general black hole that runs counter to sustainable development. My research asks, can we use the social psychological to close this gap? Based on this, we focus theoretically on the two pairs, environmental attitudes and social norms. First, environmental attitudes based on the green scale. This represents an individual's instincts. Value identification. It provides the psychological foundation for resting returns. Second, social norms. We differentiate between descriptive norms, what people must do, and injunctive norms, what social says we ought to do. The hypothesis is that these external norms moderate the attitude behind a relationship. Essentially, we believe that social pressure can transfer private beliefs into public actions. Methodologically, we employed a two-stage scenario-based experiment using Bluetooth earphones, packing damaged product in perfect working contradiction as the stimulus, as shown in the picture. Explorator 1 established the baseline with 178 validated samples. We converted that environmental attitude negative practice return intention. This was expected. Explorator 2 introduced the molding variable. We recorded 232 participants online on the divided them into 3 groups. A control group with no specific promotes, a descriptive normal group inverted of majority behavior, an injunct normal group corrective social cues. The regression analysis shows a clear hierarchy of effects. First, the mind effect is robust. Second, both norms work, but injunct norms are the most powerful habit. Here is the most critical insight, the substitution effect. As you can see the table, in the country group, attitude strongly affects behavior, 0.61. However, under high social norms, this in fact drops to 0.21 and becomes satisfactorily insignificant. Owning the margin effects of this correct norms on environmental attitudes was significant. Conclusion: social normal resemble consumer logical. External social pressure substitutes for internal attitudes when the social exploitation is occurring. Individual environmental values no longer practical behavior. People simply conform. For platforms, the takeaway is shift from passive advocacy to active architecture. Instead of just seeing big rings, we use splashy pop-ups to show that most users do not return intel lightly. Creating a green credit system also provides tangible rewards. For matches, transparency is vital. Display carbon fruiting labels and recycled material percentages on product pages make the environmental cost visible. In summary, while internal attitudes are important, external social schedules are the leader for the systemic changes. Thank you for your attention. I welcome your questions.
Dear colleagues, any questions? Please, Chen.
Thank you for your presentation. I have one question. And in your experimental design, you only use electronic product in order to control your component variables. And as we know, there are also products have a high return, such as clothing, hats, and shoes. So, do you think the software you found that can be directly used to the apparel industry? That's my question.
Oh, thank you for this brilliant observation. We deliberately choose the Bluetooth earphones because it is a standardized product with the model available, which help minimize the confounding effects of subject test or sizing issues. However, your point about this apparel sector is well taken. In fact, the literature suggests that social norms are even more powerful in high requirement socially visible categories like fashion compared to the fashion tech products. Thank you.
Thank you for your answer.
Any other questions? No. Your presentation is finished. Thank you. As far as I understand, the list of speakers has now been completed for this part of the working day of the conference. So if there is no any other presentation, so I'd like to thank you very much for the presentations, questions, and discussions. Now we probably have a lunch break, and the next part of the conference will begin at 2 p.m. Thank you.
Thank you, Chair. Thank you.
Thank you.
Thank you.
So now we will close the session,
Okay.
Zoom session. Yeah.
Okay, see you later.
See you later. Goodbye.
we are ready to start our second part of our conference.
Good day in China.
Good day, good day.
Yeah.
We have just 1 minute to wait, and after this, we start our section.
Maybe wait some time. Wait.
So, dear participants, dear authors, dear attenders, my greetings for everyone. We have to continue our part of our conference. Now we have a last section of our conference, and we have about 20-25 papers here. So, according to our scheduling, the next paper will be paper number 34, 42, 32, oh, 62. As I see, the author, the presenter is with us. So you may start your presentation, but for everyone, very important information. Please take into consideration the time limit. You have just about 10 minutes to present your scientific results and for the answer and
Go ahead. Stop.
张老师他可能网速有问题，你在你就主持一下。
Please start the presentation. Can you hear me?
Yes.
I'm online. So, my proposition to start our work. We see your presentation, which is a last one slide. So please go to the first one. Okay. Yes, everything is good. Now
Yes,
we are ready.
this is the very beginning. That's good.
I'm Jen. I'm a teacher of Singapore City. Today, my session is about the evaluation of China reflects cities. Patients truthful first study the research background of the IoT system this short translation of the evaluation. First of all, CRE has 6 cities, 100 cities. So it is seen as a transportation between China and Europe. Actually, it's actually no method, but the push up the total population. So it was focused on the development process. In order to remove these conflicts with relations is always and so we have to students in this topics and urgent topics is about testing evaluation true. Representative HQ was objective purposes. This tool for evaluation of cities. And you can see the result through the works 6 years. The evaluation system to evaluate the system distribution. There was 5 technical cities trying to Zhengzhou, Suzhou to evaluate their development levels. And these 5 technical cities were selected from hundreds of cities around the sea. And these 5 cities operate service and cover the transportation routes and work. They are also part of the key domestic routes in China. To get the date, we grab the date from 5 cities connected to the and calculate estimate. Because they standing logistic efficiency and achieve the points between high quality programs and high quality programs, efficiency and protection. It's to the top 5 cities. And Chongqing comes second, and ranked third. Suzhou and Zhengzhou takes the third place. Evaluation balance of Xi'an comes to the first because its balance progress between scale invention and transition. As a contrast, say Chongqing and Zhengzhou. And Zhengzhou, they also have they also have good travel, but suffer from efficient electronic development. So the end of the second and the first respectively. Same time, there's some quality in to the top of it from both quality and substantial innovation scale. And in contrast, how the Zhengzhou and structures. So they to improve serviceability is should have series pursue high quality development. Suzhou and Zhengzhou so clearly city and the transport driving down their own ships. So the increasing drive these cities focus their efficiency and development future. And that's my presentation.
Thank you for your presentation. Any question, please, for the presenter? Oh, I see. Please, you may ask your question.
Okay. I'm glad to answer your question. Where in your research, Zhengzhou owns the largest number of CRE roles among sample cities, but ranks last. What are the key reasons?
That's a good question. Those are cities actually Zhengzhou so largest teams around those 5 cities. However, solution with it's covered by solution. So it's with high demand. Secondly, clarity. At last, but not least, is that the viewers like accessible efficiency, which to be dropped down in time. So that's why no, it's abandonable still final to ranking. That's my third answer.
Okay, thank you. Any more question?
Yeah.
Please, one more question.
No, that's all. Thank you.
Okay, as I understand, there is no any additional questions. So thank you very much for your presentation. And now we may switch to another presentation. Next one presentation, the presentation is number 3455. 3455.
Can you hear my voice clearly?
Yes, we hear you, but we can't.
Maybe she needs. Oh yeah.
Oh, yeah, I understand. Yeah. You may start the presentation.
Could
We
everyone see my screen?
ask for all presenters to turn on the camera for the period when you have the presentation. Can you on your camera?
All right. Okay. Oh, wait a moment.
Oh,
Says
yeah.
open? Yeah.
Yes. Everything is good. We see your presentation. We see you. You may start your presentation.
Yeah. Thank you. Good afternoon, professors and fellow scholars. Today, I'm honored to present our research titled Low Carbon Logistics Development Model and the Evaluation System, using Berlin Tech Logistics as a case study. This research attempts to answer a practical question. Under the dual carbon goals, how can logistic companies reduce carbon emissions while controlling costs and maintaining service quality? Now my presentation covers 5 parts: the research background, the low carbon development model, and AHP evaluation system, the Berlin Tech Logistics case study, and our conclusions. Existing research explores green supply chain, but often leads towards macro-regional comparisons, or strictly focus on carbon accounting. For actual corporate management, a low carbon plan cannot just blindly chase emission reduction. It must also consider practical considerations, like unit transportation costs, on-time delivery rates, and customer satisfaction. So therefore, we aim to build a replicable enterprise-level low-carbon logistic evaluation framework. We established a transparent carbon accounting pathway using the GLEC framework and the ISO 14083. Furthermore, we built an indicator system that balances environmental, economic, and service performances. Finally, we evaluated the emission reduction potential brought by electrification, multimodal transport, and improved load factors. And we categorize the low carbon logistic development path into 5 types: technology-driven, structural optimization, digital empowerment, policy guidance, and a comprehensive model. Ultimately, the comprehensive model, which is emphasized multi and dimensional synergy across all these areas, is our direction we highly recommend. And our evaluation system uses a 3-tier AHP structure. At the top is the goal layer, representing the overall low carbon development level. The middle tier is the criteria layer, which balances environmental, economic, and service performance. And the bottom tier breaks this down into specific metrics like carbon intensity, unit transport cost, and on-time delivery. This structure places both carbon reduction and the realistic business operational goals into the same evaluation framework. And we used the AHP method to translate subjective expert judgments into calculable weight structures using the standard SETI 1 to 9 scale. We constructed a judgment matrix. We ensure mathematical validity by checking the consistency ratio, or CR. As long as the CR is strictly below 0.1, our matrix passes. We then multiply the certain layer weights by the local indicator weights to establish a clear global ranking of all metrics. For our case study, we select the Berlin Logistics in Wuhan regional branch and serves as a major logistic hub in central China because its core business covers city distribution, trunk transport, and warehousing management. It provides a perfect mix of urban, regional, and facility scenarios. This makes it ideal to validate the real-world applicability of our model. And to demonstrate our calculation logic, let's take light-duty diesel trucks as an example. 30 trucks traveling 28,000 kilometers a year at the 12 liters per 100 kilometers consume 100,800 liters of diesel, multiplied by our standard diesel emission factor of 2.6. This results in an annual emission of 262.1 tons of CO2 equivalent. Factoring in payload and load rates gave us 683,000 ton-kilometers. This illustrates our underlying accounting logic. And we also set up 3 scenarios for comparison. The baseline scenario assumes an entirely diesel-powered fleet. The current scenario is based on the enterprise's existing mixed fleet, reflecting current electrification progress. Finally, the optimized scenario push further by aggressively expanding electric vehicle usage, promotion road-to-rail shifts, and improving load factors. Comparing these 3 allow us to judge the true marginal emission reduction potential. And the calculation results are striking. The baseline scenario emits 8,200 tons of CO2 equivalent annually. The current scenario drops to 6,900 tons, and the optimized scenario drops further to 5,600 tons. Compared to the baseline, the optimized approach lower overall carbon intensity by a massive 28.2%. And this demonstrates the combining electrification with the transportation structure optimization yields highly significant results. And our global weight ranking reveals the top 5 priority indicators: carbon intensity, total annual emissions, a unit transport cost, a total cost of ownership, and the one-time delivery rate. This ranking shows that while emission performance is primary control target, cost constraints and service guarantees follow closely. For managers, it provides a quantified roadmap for prioritizing resource allocation. To conclusion, our study reaches 3 main findings. First, we built a standardized carbon accounting framework. Second, we create the evaluation system. Finally, our case study mathematically verified the emission reduction potential of EVs, load optimization, and intermodal transport. That concludes my presentation. Thank you all for your time and attention. Okay, now I'm happy to answer any question. Do you have any question?
Thank you for presentation. And now about the question. I see. Please, you may ask a question.
Hello. I'm glad to have this conversation with you. My question is, this paper claims to use LCA, but only includes emissions from diesel fuel and electricity consumption, while excluding vehicle manufacturing, battery production, and disposal. Does this weaken the LCA claim? And would a full LCA change the comparison between diesel and electric trucks?
Well, thank you for asking. This is a reasonable concern. True, the study follows the GLEC framework and the ISO 14083, which mainly focus on the operational emissions. Therefore, the method is close to a well-to-well or operational carbon accounting approach than a full LCA. A complete LCA would also include vehicle manufacturing, battery production, and end-of-life treatment. These upstream emissions are relatively small for diesel trucks, but more significant for electric trucks because of battery production. As a result, a full LCA would likely reduce the magnitude of the emission saving reported of electric vehicles. However, the overall conclusion would probably remain unchanged. Electric trucks still produce lower life cycle emissions than diesel trucks, although the advantage would be smaller. Further, maybe future studies should incorporate full life cycle stage to provide more comprehensive assessment. Thank you.
Thank you for your answer. More question, please?
No more.
No more question, okay.
Yes.
Okay, thank you. So,
Okay,
thank you very
thank you
much
for
for your
attention.
presentation. As far as I understand, we have to switch to next one presentation number 3468. 3468. As I see, presenter is with us. So, presenter, please turn on your camera and start your presentation as well. Maybe some problem with a connection or some delays. Okay. We see your presentation. But we can't hear you and can see you.
Good afternoon, respected chairs, professors, and fellow researchers. My name is Jingyu Zuo. I'm from Wuhan University of Technology. Today, I will present our title, a two-stage optimization for export container yard storage and allocation and yard crewing scheduling in container terminal. My presentation includes 5 parts: the introduction of the study, model development, the hyperheuristic genetic algorithm, numerical experiments, and the conclusion. With the growth of global trade, container terminals need to handle more containers within limited space and time. Shipping is still one of the most important transport modes in international trade. In container terminals, the yard area plays a key role. It connects vessel loading, container storage, and internal truck transportation. In recent years, the bottleneck of terminal operations has gradually moved from the seaside to the yard. If export containers are not stored properly, internal trucks may travel more distance. Yard cranes may also face unbalanced workloads. Therefore, in this study, we focus on the integrated optimization of export container storage allocation and yard crewing scheduling. To solve this problem, we develop a two-stage optimization model and design a hyperheuristic genetic algorithm. The main task of the first stage model is to decide which blocks should store the export containers of each vessel in its period. The objective includes two parts: reduce internal transportation cost and workload imbalance among blocks. Various practical constraints are considered in this model, such as block capacity, demand satisfaction, allocation range, workload conclusion, and variable restrictions. Through this stage, we can obtain a feasible storage plan for export containers. After obtaining the storage allocation plan, we move to the second stage model. This stage focuses on yard crane deployment and scheduling. The workload result from the first stage is used as the input. The objective is to reduce the total yard crane operation cost. This includes crane transport distance cost, fixed transfer cost, and the workload imbalance cost. Some practical constraints are also included. For example, each yard crane can only work in one block during one period. The total number of the working cranes cannot exceed the available fleet. Also, the assigned cranes must be able to meet the workload demand of each block. In this way, the two stages are connected. The storage plans determines the workload distribution, and the workload distribution feature affects the yard crane scheduling plan. Because the proposed plan has many variables and constraints, it's difficult to solve it efficiently by exact modes. Therefore, we design a hyper-heuristic genetic algorithm named HHGA. In this algorithm, the genetic algorithm works as a high-level strategy. It manages a pool of low-level heuristics. For both stages, we use inter-based encoding. The low-level heuristic pool contains 20 operator combinations. These combinations are generated by 5 Gaussian operators and 4 crossover operators. During the search progress, the algorithm evaluates the historical performance of different operators. Operators with better performance have a higher chance of being selected later. The mechanism helps the algorithm search more efficiently. The experiments are based on a parallel container terminal. The export yard has 12 blocks arranged in 3x4 layout. The planning horizon is divided into 4 periods. There are 16 vessels in the case. These settings are used to test the proposed model and the algorithm. The algorithm parameters are selected through sensitivity experiments. Each algorithm is run 20 times under the same basic settings. From the result, HHGA obtains normal objective values in GA and PSO in both tested cases. In case 2, HHGA also performs better in both the yard storage allocation stage and the yard crane scheduling stage. This indicates that HHGA can produce better solutions in a single meta-heuristic algorithm. For the yard storage allocation, containers of the same vessel are mainly assigned to the nearby blocks. This can reduce the travel distance of internal tracks and improve loading efficiency. At the same time, the workload among blocks is relatively balanced. For yard crane scheduling, most cranes stay in the same block or serve the same block for consecutive periods. Only a small number of cranes move flexibly when the workload changes. The result is reasonable because it reduces unnecessary crane movement while still meeting the operational demand. To conclude, This study investigates the integrated optimization of export container yard storage allocation and yard crane deployment and scheduling. We propose a two-stage optimization model. The two-stage optimize the storage allocation, and the second stage optimize yard crane scheduling based on the first stage result. We also design a hyperheuristic genetic algorithm to solve the problem. The numerical experiments show that HHGA performs better than standard GA and PSO in the tested case. For future study, the model can further improved by considering slope level allocation and operational uncertainty.
Thank you for your presentation. And now, question, please. As I see, we have a question. So you may ask a question.
Hello, I have one question. Why did you
Please.
choose the hyperheuristic GA to solve this problem?
Okay, thank you for your question. We chose the hyperheuristic genetic algorithm mainly because this problem is complex and highly constrained. It includes two collective stages, yard storage allocation and yard crane scheduling. A single heuristic operator may not work well for word solution structures. In HHGA, the genetic algorithm works as a high-level strategy. It can select different non-level historic operators during the search progress. So the algorithm is more flexible than a standard GA. Also, our numerical results shows that HHGA obtains better objective values than the standard GA and PSO in both tested cases. This means it's more suitable for solving this two-stage scheduling problem.
Okay, thank you. Any more questions? In this case, thank you very much again for your presentation. And now we may switch to the next one. Next one presentation will be number 34 and 82. And I see the presenter is with us.
Good afternoon, Professor. Can you hear me clearly?
Yes, we hear you. Please turn on the camera and please start your presentation.
Okay, wait a moment. Okay, can you see my screen now?
Yes, we see your screen. Is it possible to turn on the camera?
Okay, I'm ready. Good afternoon, professors and colleagues. My name is Xu Wei from Hubei University of Technology, Engineering and Technology College. Today, I'm very pleased to present our study, Financial Data-Driven Decision Optimization in Smart Logics. First, I want to introduce the research background. Traditional systems suffer from a clear disconnect between physical options and financial outcomes. Enterprises can say operational data in real time, such as GPS signal and order volume, but they still cannot observe the economic consequence at the speed. Financial reports often explain the result only after the event, rather than supporting real-time decisions. So the core questions of this study is how to turn financial data from a real view mirror into a steering wheel. Today, my presentation is organized into 4 parts. The first part is a research problem. The next part to introduce the process framework, and the third part I want to say the covers model validation, and the last part I want to highlight the decision value. First, let me begin with the problem. Today, many logistics systems are already very strong in collecting operational data, such as order time, delivery routes, and vehicle capacity. But in practice, managers care about much more than operational speed. They also care about whether the cost is too high, whether the task is financially worthwhile, and whether the risk is acceptable. In other words, logistics decisions are not only about efficiency, they are also about value. However, in many real business settings, financial data is still used mainly as a real view mirror to review results rather than a steering wheel to guide operations. This is exactly the gap our study wants to address. If we look at existing literature, AI has already been widely applied in logistics, especially in forecasting, route optimization, red line management, and digital supply chains. However, most studies still focus mainly on operational data, while financial indicators are much less embedded into daily decision loops. So, what this paper tries to aid is a missing link among finance, AI, and logistics. More specifically, the study makes three contributions. First, it treats financial indicators as active decision variables rather than only reporting indicators. Second, it proposes an integrate framework collecting financial data, AI analytics, and logistic optimization. Third, it provides preliminary quantitative verification through model expressions and simulation-based comparison. After clarifying the problem, I now move to the proposed framework. This study develops a full-layer AI logistic integration architecture. The key idea is to create a continued feedback loop that collects physical, sensing, financial data, and intelligent analytics. In other words, the model does not simply display data, but embedded financial information directly into the decision process. The first layer is financial data layer. This layer graduate cost and liquidity risk model are executed. The second layer is AI analysis layer, which use the real-time IoT and ERP function to establish foundational visibility. And the third layer is decision optimization layer. In this layer, identifies customers' value, heterogeneity, and suppose prediction. And the last layer is a performance evaluation layer where analytical outputs are translated into route adjustment and resource prioritization. Overall, this architecture creates a closed loop from data input to operational execution. In this speed, I want to make a model operational. We build four variable assumption. The first is cost, including transportation, warehousing, and unit labor or unit cost measures. The second is revenue, including order revenue and net margin. The third is risk, including reasonable days and inventory capital caption. The fourth is operations, including order volume and delivery distance. The significance of this design is that financial variables serve as the analytical core, while operational variables explain the mechanisms behind them. In this slide, present three core analytic models. first, cost prediction uses linear regression to estimate transportation cost from order value and delivery distance. Second, the risk identification uses logistic regression to estimate the probability that the account or order belongs to the high-risk group. Third, profit segmentation applied key mix clustering to grow customers or orders based on profitability and inventory-related features. The main point of this slide is to show that the study does not only propose a central framework, but also provide a clear quantitative logic. After applying the model in Fawang supply chain enterprise, we found the unit transportation cost decreases by 12.4%, warehouse utilization improved by 15%, inventory turnover rises from 4.2 to 5.1 times per year, and DSO is reduced from 35 days to 28 days. So the important point on this slide is not just the numbers themselves, but the direction of improvement they demonstrate. The next key question is how to turn those outputs into managerial action. So in this study, cost prediction suppose route planning, risk identification, suppose credit strategy adjustment, profit segmentation, suppose resource allocation priority, and inventory signal support warehouse allocation optimization. So the key shift here is very clear. Financial indicators are no longer only login record. They become forward-looking variables that can directly support managerial action. Finally, I would like to summarize the three key implications. The first is paradigm shift, moving financial data from post-event accounting to real-time AI input. The second value is management, which means differentiation, resource priority according to profit impact. The third is large-scale deployment, moving from simulation-based validation towards enterprise digital twin integration. Overall, the central message of this study is clear. Financial data should not merely record results, but should become an important input for real-time smart logistics decision. That is all my presentation. Thank you very much for your attention, and I sincerely welcome your question. Thank you.
Thank you for your presentation. As I see, we have a question, so you may ask a question.
Hello, I have a question.
Yes, please.
Thank you. My question is, how does your model handle the trade-off between operational efficiency and financial cost? Thank you.
Thank you for your question. Our model handles this trade-off by integrating both financial variables and operational variables into the same analytic framework. For example, operational factors such as delivery distance, order value, and inventory level are linked with financial outcomes such as transportation cost, warehousing cost, and capital allocation. So in this way, the model does not evaluate logistic decision only from the perspective of speed or operational efficiency. Instead, it evaluates whether the decision is also financial sustainable. Therefore, the framework helps managers balance efficiency, cost, and value in a more systematic way. Thank you.
Thank you for your answer. Any more question, please? Okay, in this case, thank you very much again. Now we have to turn on the next one presentation. Next one presentation will be presentation with number 34 and 85. 34 and 85. Oh, I see the presenter.
Okay. Hello, everyone. I'm Yu Tong. Today, I would like to present our research entitled Power Failure Recovery Strategy for Intelligent Warehouse AGV based on QR code backtracking and inertial navigation. And as you see, my presentation mainly concludes three parts. First, the introduction and the status analysis. Second, the research ideas and the technical framework. Third, the conclusion of this research. And now let's begin with the introduction. Against the backdrop of the integration of the digital economy and intelligent manufacturing, intelligent warehousing is driving the transformation from automation to intellectualism by relying on technologies such as the Internet of Things and artificial intelligence. Intelligent warehousing has become an important way to reduce logistics costs and improve supply chain efficiency. As the core executive unit of intelligent warehousing, automated guided vehicles, or AGVs, are widely used in e-commerce manufacturing and cold chain logistics because of their autonomous navigation and flexible collaboration capabilities. They undertake important tasks such as material transportation and order fulfillment and have become essential to modern warehouse operations. And at present, the application of AGVs have achieved larger scale application, integrating technologies such as laser SLAM navigation. AGVs have largely replaced manual handling, solved the pain points of high labor costs and low efficiency, and adapted to the needs of different warehouse scenarios. However, during the long-term high-load operation of AGVs, sudden power failure problems occur frequently due to grid fluctuations, factory abnormalities, and other factors, which directly lead to operation interruption and control system shutdown, and even trigger a series of problems such as positioning deviation, equipment damage, and safety accidents. Theoretically, combining the advantage of accurate data traceability of QR code backtracking with the characteristics of no external dependence and the high precision short-term positioning of inertial navigation enriches the research system of AGV for emergency disposal and the hybrid navigation technology, and provides new technical ideas and theoretical references for the power failure recovery research of semi-automated equipment. So in intelligent warehousing scenarios, emergency situations may cause the central control system to cut off power to all AGVs. After power restoration, three major problems arise. And so you can see first is positioning loss. Before a power failure, AGVs determine their positions through real-time QR code scanning. After power failure, global coordinates are lost. Although IMU sensors can estimate movement, their errors accumulated over time and cannot satisfy the high precision requirement of distance warehouses. And second is the task interruption. The progress of uncompleted tasks is lost due to power failure. After power restoration, AGVs may repeat completed tasks or skip key steps, which will cause order confusion and the inventory data error. And third is the inefficient recovery. If every AGV independently performs relocation and task planning, recovery may take several minutes, which directly affects warehouse efficiency. So in summary, positioning loss, task interruption, and inefficient recovery are the three core challenges that must be solved. So to address these challenges, we propose three corresponding solutions. For high precision positioning, we adopt a strategy of data fusion positioning and QR code correction. The AGV records the last scanned QR code before power failure and uses IMU data to estimate its trajectory. After returning to the vicinity of the recorded QR code, it performs QR code rescanning and calibration, reduce positioning error to within plus or minus 2 centimeters. For task recovery, we adopt key data storage and dynamic task verification. Important information such as task progress and movement history is stored before power failure. After recovery, the central system verifies task status and resumes unfinished tasks seamlessly. For efficient recovery, we adopt a dynamic priority allocation and phased recovery. The system schedules AGVs according to task urgency and path length, ensuring fast and conflict-free recovery. Together, these strategies form the core framework of our solution. So now let's see this. Figure 1 is a flowchart, and this flowchart illustrates the overall recovery framework proposed in this research. Before power failure, the system continuously records 3 types of key information. It's the QR code coordinates, IMU, trajectory data, and the task progress. These data are stored in FRAM memory together with the time step information. A supercapacitor provides backup power to ensure reliable data preservation even after sudden power loss. Through these preparations, the AGV retains sufficient information for accurate recovery after power restoration. And now is another figure. The figure 2 shows the emergency protection process when a power failure occurs. Once power failure happens, the system simultaneously performs data protection and hardware protection. Critical information is stored in FRAM memory, while the AGV locks its wheels and activates backup power. These measures ensure operational safety and prepare the system for the subsequent recovery. So next, I will introduce the operation process after power restoration. First, we can see that the backward integration and path planning. The AGV reads the previously stored IMU data and reconstructed a trajectory before the power failure. The purpose of backward integration is to estimate how the robot moved before shutdown and generate a backtracking path. Second is the motion execution and the mechanical control. The AGV moves along the generated path at a low speed of 0.3 meters per second. During movement, closed-loop control continuously tracks trajectory deviation and improves recovery stability. And third is about the deprecation strategy when approaching Q_last. When approaching the Q_last position, the AGV slows down further to ensure accurate QR code scanning. And last is about the positioning calibration. After arriving near Q_last, the AGV rescans the QR code and compares the actual coordinates with the estimated coordinates. Its correction process eliminates accumulated IMU errors and achieves centimeter-level positioning accuracy. And to verify the effectiveness of the proposed strategy, we conducted a series of simulation experiments, as you see in the table. It's about a total of 100 power outage events was simulated. The AGVs were required to return to the Q_last position independently and complete QR code correction. experimental results shows that the IMU positioning error remained within 5 centimeters, while the final positioning error of the QR code correction was controlled within 2 centimeters. The recovery time of a single AGV was less than 20 seconds, and recovery efficiency met the expected requirements. In addition, human intervention was required in less than 5% of cases. These results demonstrate the effectiveness and reliability of the proposed recovery strategy. And so, at last, to conclude the whole research. In this research, we focus on the problem of AGV operation recovery after sudden power failure in intelligent warehouses. The main conclusions can be summarized in 3 aspects, as you see. First, we identified 3 major challenges caused by power failure: positioning loss, task interruption, and inefficient recovery. Second, we propose a complete recovery framework integrating QR code backtracking, inertial navigation, task verification, and dynamic scheduling. Third, experimental results verify that the proposed strategy can achieve high positioning accuracy, reliable task recovery, and efficient system scheduling. These all results demonstrate that the practical value of the proposed method for intelligent warehouse application. And so now that concludes my presentation. Thank you very much for your attention and time. I sincerely welcome any questions or suggestions from all of you. Thank you.
Thank you too. I see we have a question, so you may ask a question, please.
Okay. First, thank you for sharing. I have a question. It's about in multi-AGV power outage recovery scenarios, why adopt a layered dynamic priority plus phased recovery strategy instead of restarting all units uniformly? That's my question.
Okay, thank you. Thank you for your question. Is that if all AGVs restart simultaneously after a power outage, problems such as path conflicts, intersection congestion, communication overload, and task deadlocks may occur, which significantly reduce recovery efficiency. Therefore, we adopt a layered dynamic priority and phased recovery strategy. AGVs are prioritized according to task urgency and remaining path length, ensuring that important tasks are resumed first. At the same time, positioning and path replanning are carried out in stage, which reduce communication pressure and avoids resource conflicts among multiple robots. So as a result, more than 90% of AGVs can successfully resume operation within 2 minutes while maintaining overall system stability.
Oh, thank you for your answer. I get it. That's all from me.
Okay, thank you.
Thank you.
Thank you. Any more questions, please? As I see, we don't have any new questions, so thank you very much for your presentation. And now, dear attenders, dear colleagues, I have a proposition to change the order of the presentation. And the next one presentation, I propose the presentation number 20,261. Yuri Kalin. According to our schedule, we just have to change the order of presentation, yeah. And after this, we will return to the normal order of the presentation. So, Yuri, as I see you are with us, and you may start your presentation.
Sure. Yeah, let me share my screen, please. 1 second.
Yes.
Sure.
I give you possibility to share your screen.
Oh, thank you. Can you see
Yes.
Awesome. Yeah.
So we try to make it for a full screen.
Okay,
not for the part screen, but for the full screen.
Mm-hmm. Is it okay now?
Oh, everything is good. You may start your presentation.
Yeah, thank you very much again. So let me start from the very beginning. Hello again. My name is Yuri. I'm presenting our paper, Intelligent Multispectral Video and Analysis System of Human Detection and Injury Classification based on Deep Learning for Rescue Operations Tasks. In emergencies, disasters, fires, combat zones, response time is critical. Even a few minutes delay can increase mortality. Yet traditional RGB cameras fail in smoke, dust, or low light and provide only passive observation. They cannot assess the psychological state of a victim. We need an automated system that detects people and classifies injuries in real time, even under harsh conditions, like smoke, dust, low lighting, etc. So the system follows a 7-stage pipeline. First, an RGB camera and an infrared camera captures synchronized frames. Second, the frames are pre-processed, noise is filtered, and images are normalized. Then the two sensor streams are specially registered and fused into a single multispectral representation. Then a deep neural detector localizes human bodies. On the 5th stage, each detected person's region of interest is cropped and features are extracted. Then a classifier identifies the injury type and estimates severity. Then in our pipeline, we have digital injury markers, location, class, and severity are passed to the emergency decision support system. Importantly, all processing runs on edge computing node directly at the scene, not on some far server. So only results, not raw video, are transmitted, keeping latency under 40 milliseconds. So we can do this with in real time with 25 frames per second. Let me briefly describe our formal model. The input is a multispectral video stream V of paired RGB and infrared frames. After preprocessing and special registration, the two channels are fused as alpha times RGB plus beta timer infrared. A detection model D that finds bounding boxes. For each box, a feature extractor produces a vector. A softmax classifier assigns injury class CI, and the sigmoid functions outputs a continuous severity score SI between 0 and 1. The complete pipeline is written as M equals G of B as a single composition of all stages. Training uses a combined loss functions. L total equals lambda times the EOU detection loss plus lambda 2 times the cross-entropy classification loss plus lambda 3 times the MSE severity loss. And the ADAM optimizer minimizes this joint objective. The core network is 3D CNN, multispectral classifier, chosen because it processes spatial and spectral dimensions simultaneously. The input tensor is batch spectral bands 64 multiplied by 64. After 3D convolution max pooling and 2 fully connected layers with dropout, the output is softmax probability over the 5 injury classes. So our experimental results. The proposed model achieves 94% precision, 93% recall, and F1 and MAP of 0.93 and 0.92, and processes video at, as I said before, 25 to 40 frames per second, meeting real-time requirements. The comparison chart shows our model outperforms all baselines. faster RCNN at 0.88, yellow V5 at 0.90, and retain net at 0.89, CNN with thermal data at 0.92, and the transformer detector at 0.94. Our multispectral fusion model reaches 0.96 accuracy. The advantage is most pronounced under low illumination, smoke, and so the ablation study reveals the contribution of each component. A baseline RGB only CNN reaches 0.86 accuracy. Adding data augmentation gives us about 2%, and adding the infrared channel adds another 4%. So it's one of the most important parts of our work in our pipeline. The multispectral fusion module contributes plus 4 to 5%. The severity estimation branch adds a final 2%. The full model achieves 96% of accuracy, a total improvement of 5 to 8 to 12 over the RGB without infrared that we are talking about now. Now we have some results in charts. So the comparison charts confirm that same trend across all metrics: accuracy, precision, recall, and MAP. Our model achieves the highest value in every metric. The training and validation loss curves converge smoothly over 20 epochs without overfitting. So, yeah, training accuracy and validation loss you can see here on this slide. Now about injury classification. The confusion matrix covers 5 classes: burn, bleeding, fracture, bruise, and healthy. Most samples are correctly classified. The only notable confusion is between bruise and bleeding. These cases each, which is expected, as the injuries look similar in both visible and infrared spectra. So again, if we see some smoke or something and we need some extra channel of data, and this infrared idea of infrared usage to analyze this data is important here. And yeah, so practical value and limitations. The system has direct applications in emergency response, disaster medicine, search and rescue, military medicine, and UAV-based aerial monitoring. Limitations include reduced performance under extreme atmospheric conditions, limited training data for the rare injury types, and sensitivity to camera obstructions. Future work will focus on deeper networks, UAV integration, and federated learning. To conclude, our multispectral system achieves 96 accuracy and 93 recall, improving our over RGB only method by 8 to 12%, while processing video in real time at up to 40 frames per second. The system is robust to smoke, dust, and low light, conditions critical for real rescue scenarios. This, I think this is the last my slide. Yeah, so we have maybe some questions. Thank you very much.
Thank you very much for your presentation. Any question, please? Is there not any question? I'd like to ask you the question. How does multispectral imaging can improve rescue detection, for example?
Yeah, thank you very much for your question. So, the main idea is to combine visible RGB information with infrared thermal information. So the system can detect not only shape of a person, like in using RGB data, but also thermal anomalies. For example, some tissue-related features that are not visible in normal cameras. And this is very especially useful in smoke, light, low light, in dust, and partial occlusion. So in our results, this multispectral approach gave us 8 to 12% better results compared with the just ordinary RGB data. Thank you.
Thank you for your answer. I'm quite satisfied with your answer. Any more question, please? Okay, so in this case, thank you very much again for your presentation. Now we'll switch back to our order of presentation. And I would like to give a floor for the next one presenter with presentation number 3493. As I see, presenter is with us, so please start your presentation.
Good afternoon, respected experts and dear colleagues. My name is Wu Shan from Hubei Open University. Today, I'd like to present my paper. Next, I will unfollow our research framework and co-findings step by step. First of all, let's start with the research background. Booming e-commerce fuels surging cold chain demand. Yet last mile delivery becomes the priest, complicated supply chain segment, restricted by strict temperature control, punctual activity, and personalized time windows. Most enterprises depend on empirical shadowing, cause high costs, and up to 15% fresh goods loss. To solve these problems, we built an optimization model while operation research. After literature review, 3 research gaps are found. Unique nature of temperature loss, correlations, lack of large real data verification, and insufficient algorithm comparison. Such 2 questions: how to construct a full objective integrated model and how to design an algorithm balancing accuracy and efficiency. To fill these gaps, we target MILP modeling, hybrid algorithm design, and real data validation. Our 3 contributions: a full objective integrated model, an exact heuristic hybrid algorithm, and a statistically verified practical experimentation. Existing cold chain VRP includes capacity, time window, and spoilage limits, but free integrate exact and heuristic algorithm refined by big data. Ruby optimizes small cases, while GA fits large ones. Without benchmark, we combine both to offset drawbacks. The table contrasts our study with prior literature in 4 aspects. 4-dimensional optimization targets embedded temperature decay constraints, hybrid algorithm design, and statistical experiment verification, which constitute our core innovations. Now, for the mathematical model. 1 depot, several transit harbors, and customers. Identical vehicles, customer time windows, and temperature-related spoilage. We minimize transport, inventory, penalty, and decay costs, and the basic constraints to build the MILP model. Our model simplifies to NP-hard CVRP. Calculation difficult, surges with scale, and solvers struggle on large cases. Hence, we adopt a hybrid algorithm for balance of accuracy and efficiency. We propose a two-stage hybrid algorithm. Gurobi solves small or medium cases for benchmarks and improve GA, optimizes initialization, elite rentation, and local search for large-scale problems. We test our algorithm on TEL I7 with 3 real date-based instances. We compare our method against manual shadowing on cost, punctuality, empty load, and damage rate. Our method outperforms traditional shadowing significantly. Total cost down 20%, delivery time over 22%, empty load and spoilage cut by over 60%. We benchmark solvers on various scales. Gurobi optimizes small instances fast, but has a 9% gap for large cases in an hour. Our improved GA finishes in 185 seconds with only 2% gap and 20% cost saving, verifying the hybrid strategy's superiority. We analyze Gurobi conversions on middle M1 instance. Upper bound falls, lower bound rises, proving its accuracy for small and medium problems. This slide compares GA and improved GA via conversions curves. First, improved GA converses at 120 generations, 27.3% faster, vs originally 165 generations. Second, its optimized cost drops by 1.5% for better economy. Besides, its average fitness is near to optimal, strengthening global search performance. Sensitivity analysis on transport cost, delay penalty, and vehicle capacity shows the model is slightly sensitive to transport cost and keeps stable outputs, verifying its robustness. We contrast a valid MILP model and efficient hybrid algorithm experiments with statistical verification, reduce costs and spoilage notably. The work quantifies cold chain deterioration theoretically. Future research covers 3 directions: dynamic routing via real-time IoT data, deep learning assisted optimization, and multi-temperature zone model existence. That concludes my presentation. Thank you.
Thank you for your presentation. Questions, please, for the presenter.
Hello. Why was the temperature decay coefficient excluded from sensitivity analysis alongside transportation cost, time penalty, and vehicle capacity? And would variations in temperature parameters significantly alter the optimized cargo loss outcomes?
Thank you for your available question. We agree the temperature decay coefficient is critical to cargo loss. We only see later transportation cost, time, penalty, and vehicle capacity for sensitive tests in this paper. Due to limited experimental workload, we plan to add it in follow-up research. Thank you.
Thank you for your answer. One more question, please. As I see, we don't have any new questions, so thank you very much for your presentation. And according to our scheduling, next one presentation will be presentation number 3496. 3496. As I see, the presenter is visible, so please start your presentation. And also please turn on the camera. Sorry, we don't hear you. Please turn on your microphone as well.
Oh, sorry.
Oh, everything is good.
Good afternoon, everyone. I'm Fu Meng from Wuhan Technology and Business University. My presentation topic is layout optimization of the Douyin supermarket warehouse in Wuhan using the system layout planning method. Let me start with the background. Douyin is moving beyond interest-driven e-commerce by launching a shelf-based supermarket model, competing directly with Tmall and Jingdong supermarkets. So why we choose Wuhan for the study? Wuhan is a key commercial hub in central China. The warehouse here directly affects delivery speed, operating costs, and the regional competitiveness for Douyin supermarkets. So optimizing this layout is both timely and important. Now here is a quick overview. The warehouse was set up in March 2024. It covers 26,000 square meters and originally had 11 functional zones, including 6 core operational and 5 luxuries. And here are the key material flow before optimization. Please look at the table. We can see that the two biggest bottlenecks are inbound to storage and the storage to picking, which shows 9,520 units over 125 meters, and the storage to picking shows 8,765 units over 120 meters. These long distances are the main problem.
我去开会，你做你的卷子，做完再说。
We identified two critical issues. First, the redundant function zones. The temporary work zone takes up 2,340 square meters. That is 9% of the whole warehouse, but it's only used during big promotions. The rest of the time, it just sits idle, wasting space and causing unnecessary cross-zone trips. Second, the inefficient coordination. Large gaps between high-frequency zone pairs, especially the inbound storage and the storage to picking, make goods travel too far, which drives up material flow in density. So we used SLP method. Step 1 is PQRST analysis, converging product quantity, routes, support, and time. Now let's move on to the key steps. The step 2 is the logistics relationships. We classified flow intensity into 5 levels: A, E, I, O, and U. The A levels means absolutely necessary, goes to storage to picking and inbound to storage. And the E level goes to packing to the outbound. And the table shows the full breakdown. The next step is the non-logistics relationships. We looked at 6 factors: workflow consistency, equipment compatibility, information timeliness, supervision is safety, and cleanliness. Rating came from the marginal interviews. And step 4 is the comprehensive scoring. We combined logistics and non-logistics with a 2-to-1 weight because physical flow matters more. The final grade is, we can see that the storage to picking and the inbound to storage both got A, and that is 11 to 12 points. And the inbound to quality inspection and packing to outbound got E. These scores guided our layout decisions. Now please look at the two figures on this slide. The comprehensive interrelationship diagram shows the closeness rating between every pair of function zones. The trickier the line, the more important it is to put those zones next to each other. For example, the storage and picking have the strongest connection. That's why they must be adjacent. And the function zone location diagram translates those relationships into an actual spatial arrangement. It tells us where each zone should be placed relative to others. Following these diagrams, we redesign the layout. And this brings us to the two specific changes shown below. First is the eliminate of the temporary work zone. It looks up 2,340 square meters, but was barely used. Removing it frees up space to the core storage. For peak times, we will use dynamic console location instead. The second is the merge spare zone into the packing zone. The spare parts zone stores box, tapes, things that feed directly into packing. Merging them cuts handling detours and reduces the layout from 11 down to 9 function zones. After the optimization, distances got much shorter. Please see the table. For example, the inbound to quality inspection drops from 150 to 65 meters, and the storage to picking went from 120 to 100 meters. Total routing distance falls from 785 to 575 meters. Now is the results. The total material flow intensity before was about 3.31 million unit meters. After, it drops to about 2.58 million. The reduction is about 22%, which proves that our SLP-based redesign really works. Finally is the conclusion. In this paper, we applied SLP method and developed an evidence-based optim layout. By removing the temporary work zones and merging spare parts into packing, we cut total material flow intensity by 22% and significantly improved inbound and outbound efficiency. This provides a practical, repeatable framework for emerging the e-commerce logistics standards, especially those growing fast with fragment early-stage planning. That's all my speaking. Thank you for your listening, and I'm happy to take any questions.
Also, thank you for your presentation. As I see, we have a question, so you may ask a question, please.
Well, thank you for excellent presentation. I have a question regarding your optimization, which is based on static data and does not consider seasonal demand fluctuations or promotional peaks. Can this static layout still work well under dynamic e-commerce conditions? should flexible or configurable layouts be considered? That's my question.
Okay, thank you for your question. You are right. This is a limitation of our study because our optimization targets the average daily operation using data. So we use the data from the normal weeks. For routine days, the layout works well. But for the promotional peaks like Double 11, the Douyin supermarkets already using temporary measures such as adding staff and mobile sorting tables. So our removal of the permanent temporary zone actually released space for such flexible adjustments. In the future, we can go further by introducing modular racks and dynamic sorting, which would allow quick reconfiguration of the warehouse based on the real-time demand. So static SLP gives us a solid baseline, and flexible design is the next step we plan to explore.
Oh, well, thank you for your answer. That's all my question. Thank you.
Okay.
Any more question, please? Okay, as I see, we don't have any new questions. So in this case, thank you very much for your presentation.
Okay,
and now,
thank you.
According to our order, I would like to invite the next presentation, the next presenter with the presentation number 3499. And after this presentation, we also will change the order. So the current presentation is.
Okay, I'm
We hear
coming.
you. Yes, yes.
I can share the screen.
Please share your screen.
Okay. Okay. Can you see the screen?
We see the screen. Please continue. Start your presentation.
Okay. Good afternoon, everyone. My name is Xu Qing. I'm from Wuhan Business University. Sorry, screen. Okay. I'm coming from Wuhan Business University. It is a great honor to be here today to present our research findings. Today, my presentation title is Logistic Demand Forecast of Fresh Agriculture Product in Hubei Province, based on combined forecasting model. My presentation are divided into 4 parts. The first one, research, background and objectives, and the third, forecasting methods, and the third, key findings, and the fourth, conclusion and countermeasures. Let's begin with the research background. As we know, Hubei is a major agriculture province in central China. Its output of fresh product is consistently rising, establishing it as the crucial nation production base. Furthermore, the industry is developing at a remarkable pace. In 2024 alone, online sales of fresh agricultural product in Hubei reached an impressive 1.14 billion yuan, signaling a vast and largely market potential. However, The rapid growth reveals a critical bottleneck: logistics. Fresh products are highly perishable and have high transportation costs, creating an urgent need for a more efficient and reliable logistics system to support this thriving industry. Therefore, the primary objective of our study are twofold. First, to significantly and accurately forecast the logistic demand for fresh products in Hubei over the next 5 years. And the second, to provide robust, data-driven support for decision makers in optimizing resource allocation. The dreaming process and controlling cost ultimately foster the high quality development of the entire sector. Okay, the second part, forecasting method. To achieve these objectives, we employed a sophisticated research method, a combined prediction model. Why a combined model? Because every single model has its limitations. By integrating different methods, we can use their respective strengths and significantly improve the overall accuracy of our forecasting. Okay, here is the basic data. The year is from 2040 to 2024. And we get the data from the Hubei Statistic Yearbook. Okay, the first method, the quadratic exponential smoothing model. A time series model known for its ability to capture long-term trends in data. Its role in our combination was to correct any potential deviations in long-term projections from other models. And here is the result from this model. The initial value is 532 million point 867, and the alpha is 0.3, and the result showed the error is minus 0.85%. That's a very small error. And the second, we use a gray model, which is particularly adept at handling scenarios with small sample size and incomplete information. It effectively compensates for the exponential smooth methods shortcomings in such case. And here is the result. And we use the development coefficients. A is minus 0.026, and gray action quality B is 505 million. And the result shows the average error is minus 1.03%. That's a very small error. And finally, we use a combined risk prediction method, the reciprocal variance weighting method. The weight for each model was assigned using this method, which logically gives more weight to the model with smaller prediction errors. The result was a weight of approximately 60% for the exponential smoothing model and 40% for the gray model 1-1. The result was remarkable. The average prediction error of our combined model was a mere 0.76%, which is clearly better than using either model alone. Now let's move to our key findings. The most prominent conclusion is that during the fifth 5 years plan period, the logistics demand for fresh agricultural products in Hubei will exhibit a steady and robust growth trend. Our model predicts a starting demand of 68.669 million tons in the year 2025. The demand is projected to rise to 76.99 million tons by the end of the period in 2030. This represents a substantial net increase of 8.10 million tons over 5 years. What does this mean for the market? It is clearly indicate that there is still enormous untapped potential in the fresh agricultural product logistic market. More importantly, it signals a strategy shift to the industry from rapid expansion to high quality steady growth. Our second finding focuses on the growth trend itself. As you can see from the chart, the combined forecast provide a more stable and reliable projection. We observe that the annual year-on-year growth rate will remain stable, fluctuate between 2.22% and 2.47%. The slight slowdown in the growth rate is not a cause for concern. Rather, it represents the new normal as the market matures. A significant shift from quality to quantity and efficiency. This transition represents both challenge and opportunities. It places higher demand on the logistics industry to become more refined. Specialization and intelligence of logistics service. At the end, the conclusion. The core conclusion, the logistic demand market for fresh agricultural products in Hubei province has broad prospect, but the development model urgently need an upgrade. The first one, improve cold chain infrastructure to reduce circulation loss. Accelerate the construction of pre-cooling, warehousing, sorting, and processing centers at production sites. Build a closed-loop process of pre-cooling at a region. Cold chain storage, cold chain transportation, terminal delivery. And second, build an efficient multimodal transport system to reduce comprehensive cost. Leverage Hubei's advantage as the thoroughfare of 9 provinces to integrate road, rail, water, and air resources. Develop road, rail, and rail water combined transport to reduce transit links. And last, promote the initial and intelligent upgrading of logistics to enhance operational efficiency. Establishing a provincial logistic information platform to achieve intelligence matching of vehicle good and warehousing. Promote technologies such as full process traceability and intelligence temperature control. That's all. Thank you for your attention. Now,
Thank you for your presentation. Thank you for your presentation. And yes, I see we have a question, so you may ask a question.
Okay, I have a question. In your combined forecasting model, the weights for the two original models are different. Could you please explain how the weights were determined?
Okay, thank you for your question. In the combined logistic forecasting model, we determined the weights using a method called the reciprocal variance weighting method. The core idea is quite straightforward. We assign a high weight to the model that demonstrates a smaller prediction error. In other words, the more accurate a single model's historical performance is, the more influence it has on the final combined forecast. In our specific case, this method resulted in a weight of about 60% for the quadratic exponential smoothing model and 40% for the gray model. This approach allowed us to efficiently leverage the strengths of both methods, resulting in a very low average prediction error of just 0.76% for the combined model.
Oh, thank you for your answer.
Thank you for your answer as well. Any more questions? No. As I see, we don't have any new questions. So thank you very much for your presentation, for the answer on the questions. And now also give me possibility to change the order of our presentation. I would like to give a floor for the Yuri with his presentation number 20,2065. Please, Yuri, it's your time to perform your presentation.
Yeah, thank you very much. Let me share my screen.
A moment. I give you this possibility. So
Yeah,
you can start the presentation.
Thank you. Yeah. I think you can see my screen now.
Yes, We see your screen. Please make it for the full screen.
Yeah, sure.
Okay,
So
everything is good.
yeah, thank you. So I'm going to present our work entitled Deep Learning Methods for Anomaly Detection in Large-Scale Datasets. This research focuses on the application of modern deep learning techniques for detecting anomalies in brain MRI scans, magnetic resonance imaging scans. In particular, we compare several neural network approaches, including variational autoencoders, generative adversarial networks, and transformer-based models. The main idea of the study is not only to detect pathological changes in medical images, but also to compare these approaches under the same experimental conditions. This is important because medical imaging data is complex, high-dimensional, and often difficult to label manually. So medical imaging technologies such as MRI, computer tomography, X-ray are developing very rapidly. As a result, hospitals and diagnostic centers generate a huge amount of visual medical data every day. Brain MRI is especially important because it allows doctors to visualize soft tissues and detect tumors and other pathological changes without invasive procedures. However, the increasing volume and the complexity of MRI data creates serious challenges. Anomaly detection is especially useful in this context because many pathological cases are rare and difficult to describe as fixed classes. Instead of training a model only to recognize predefined diseases, anomaly detections allow us to learn what normal brain structure looks like and then detect deviations from it. So deep learning is well suited for this task because it can automatically extract complex features from an image data. So the problem it addresses in this work is anomaly detection in brain MRI images. And anomalies in medical images are often, as I said, poorly defined, and that's why in many cases there is not enough labeled abnormal data to train a classical supervised learning model. This makes traditional supervised classification less suitable for this task. If the model requires many examples of each disease class, it becomes difficult to apply it to rare and unusual pathologies. Therefore, unsupervised and semi-supervised methods are more appropriate. These models can be trained mainly on normal samples. After learning the distribution of normal data, they can identify samples that significantly differ from this learned distribution. In our study, anomalies are detected through reconstruction errors, likelihood estimation, prediction errors, or deviations in learned contextual representation. Research gap. Although many deep learning methods have already been applied to anomaly detection, there is still an important research gap. Most existing studies evaluate models separately. For example, one paper may test a variational autoencoder on one data set with one preprocessing pipeline, while another paper may test a generative adversarial network or some other models. This makes it difficult to compare the real performance of these models fairly. There is also a lack of unified benchmarking that includes probabilistic generative models, adversarial models, and attention-based architectures within the same experimental setup. Therefore, our study focuses on a unified comparative evaluation of VAE, JN, and transformer-based models. The goal is to understand their strength and limitations under identical data conditions. So key contributions of this study is a unified experimental framework for comparing three deep learning approaches: variational autoencoders, generative adversarial networks, and transformer-based models. The study includes a standardized preprocessing and training pipeline. This means that all models are evaluating using the same general conditions, which makes the comparison more objective. We also use standard evaluation metrics such as accuracy, precision, recall, and F1 score. Traditional anomaly detection methods include statistical techniques, clustering methods, and classical machine learning algorithms. Examples include PCA, key nearest neighbors, local outlier factor, 1 plus SVM, and isolation forest. These methods are relatively simple and computationally efficient, especially for low-dimensional or structured datasets. However, they have serious limitations when applied to medical images. Brain MRI scans are high-dimensional, non-linear, and visually complex. Classical methods often require manual feature engineering, and they may fail to capture subtle spatial dependencies in the data. Deep learning methods overcome some of these limitations because they learn hierarchical feature representation automatically. This is why models such as VAE, GAN, and transformers have become highly relevant for modern anomaly detection tasks. So this slide summarizes the main strengths and limitations of the considered methods. PCA is simple and fast, but it has limited ability to model non-linear relationships. One class SVM can work when only normal data is available, but it is sensitive to kernel selection and has scalability problems. Isolation forest is efficient and scalable, but it may not capture complex feature interactions. Variational autoencoders are useful because they learn compact latent representation and support data generation. However, their reconstruction quality may decrease when anomalies are complex. GANs can generate realistic synthetic samples and support data augmentation, but they may suffer from training instability and more collapse. Transformers can capture long-range dependencies and global contexts, which is very important for medical images. However, they require more computational resources. So our methodological pipeline begins with data collection. In this study, the main focus is on brain MRI scans, as I said before, and the time series data is also considered in the general framework. Before model training, the data is pre-processed. This includes normalization, artifact removal, standardization, resizing, and noise reduction. The important point is that the models are trained mainly on normal samples. This allows the model to learn the baseline distribution of healthy or typical data, to use it then to understand and to find these anomalies. During inference, the model receives a new sample and computes an anomaly score. Depending on the model, this score can be based on reconstruction error, likelihood, prediction error, or attention-based deviation. If the anomaly score exceeds a defined threshold, the sample is classified as anomaly. So variational autoencoders are probabilistic autoencoders that learn a structured latent space. During training, the VAE minimizes combined loss functions. This includes reconstruction loss and KL divergence. The reconstruction loss measures how well the model can reproduce the input image, while KL divergence regularizes the latent spaces. Generative adversarial network, GAN, are based on the interaction of two neural networks, a generated and a discriminator. The generator tries to synthesize realistic MRI images, while the discriminator tries to distinguish generated images from real ones. And for anomaly detection, samples that deviate strongly from the learned normal distribution can be classified as abnormal. transformer-based model. These models rely on self-attention mechanisms. In image analysis, transformers are often implemented as vision transformers. The image is divided into patches, and these patches are processed as a sequences. This allows the model to analyze not only local image features, but also the global context. That is very, very important, and you will see it in the following slides. So we have evaluation metrics, the following evaluation metrics: accuracy, precision recall F1 score, ROC AUC, reconstruction error, computational cost error, and our experimental setup is the following. So to ensure a fair comparison, all models were evaluated within a unified experimental pipeline. The study used publicly available brain MRI data, including the BRATS dataset, which contains MRI scans with healthy and pathological cases, including brain tumors. All images were resized and normalized. As I said before, standard pre-processing steps, including noise reduction, intensity normalization, and format standardization. This setup makes it possible to compare all three methods under equivalent conditions. So we have the following performance metrics. The slide presents the quantitative results. The transformer model achieved the best performance with an accuracy of 0.90 precision, of 0.88 recall, of 0.91, and F1 score of 0.89. The result can be explained by the ability of transformer to model global spatial dependencies in MRI images. For medical image analysis, this is very important because tumors and other abnormalities may have complex spatial structures. The GAN model also demonstrated strong and stable performance, but it achieved an accuracy of a bit less, like 0.85, and recall of 0.89. So the high recall indicates that GAN-based anomaly detection can reduce false negatives, which is especially important in medical diagnostics. The VAE showed lower performance with an accuracy of 0.78 and F1 score of 0.77. However, it remains valuable because it provides interpretable anomaly assessment through reconstruction error and can be used as a baseline generative model. So, conclusions. The experimental results confirm that modern deep learning methods are suitable for modeling complex medical data distributions and detecting pathological changes in brain MRI images. Among the evaluated models, transformer-based architecture achieved the best quantitative results. It demonstrates the highest accuracy, recall, and F1 score. In the same time, we have some limitations in future work. Despite the promising results, several limitations should be mentioned. First, the study mainly focuses on brain MRI data. This means that the result may not directly generalize to other medical imaging modalities, such as computer tomography or X-ray. The performance of deep learning models strongly depends on dataset size and quality. In real clinic environments, data may be noisier, more or less standardized. Third, transformers model requires significant computational resources, which may limit the application in some practical medical systems. Our future research should focus on, and will be focused on, extending the comparative framework to multimodal medical data. It would also be useful to include larger and more diverse data sets. So thank you for your attention. Maybe you have some questions. Thanks.
Thank you for your presentation. And I see you have a question, so you may ask a question, please. Please ask a question. Would you like to ask a question or not?
Okay, thanks for your speech, and I have some question.
Yes, please.
Yes. I think that you concluded that the transformer models achieve the best performance in your study. Could you please elaborate on what specific aspects of the transformer architecture contribute the most to its high recall and accuracy of the MRI anomaly detection?
Yeah, thank you very much for your question. So the main reason is the self-attention mechanism, I guess. So it allows the transformer to analyze not only local regions of the MRI image, but also the global spatial context. So in brain MRI, pathological changes can be connected with relationships with distant areas of the image, not just one part and some close areas around. And the transformer models divide the image into patches and compare these patches with each other so they can be better capture long-range dependencies. This helps the model detect subtle abnormal patterns and reduces false negatives. This is why in our experiment, the transformer achieved the highest recall and accuracy compared to two other models. Thank you.
Okay, I understand it. Thank you for your answer.
Thank you.
Thank you. Any more question, please? So if we don't have any new questions, thank you very much again. And the third one presentation will be some later. So let me switch to our classic order of the presentation, and I would like to invite the next presenter, presentation number 34 and 80. As I see, presenter is with us, so you may start the presentation.
Yes. Can you see my screen?
Yes, everything is good.
Okay, great. Okay. Good afternoon, everyone. My name is Li Liu from Wuhan University of Technology. My presentation title is Design and Quantitative Evolution of a BOPPS Informed Blended Learning Module. I know many papers in this conference focus on AI algorithm, deep learning, or the mobilization. My study has a connected perspective. We focus on how an engineering course can generate learning data and how this data can support AI-assisted dialogues and feedback. In other words, our work is an AI-enabled learning analytic framework for engineering education. So here is the outline. So we'll start at the introduction. We treat our course as a learning analysis pipeline. Learning activities continuously generated activity data. This data can be transformed into features for engagement analysis, learning profiles, and future predictive modeling. In our study, we collected three complementary data streams from 30 students with an average task completion rate of over 19%. This provides data for quantitative evaluation and future AI-enabled applications such as risk prediction and personalized feedback. We use a BOPPS structure to achieve a closed loop data workflow. And before we started our work, we want to explain why there are many problems with micro-joining course. The course covered, as we can see, the course covered multiple subjects. Students need to connect to many abstract mechanisms. And in a traditional lecture, we may only observe the final grades. So a data-driven approach asks a different question. So can we observe the learning process? Can we represent it as features? Can we interview students' engagement of risk? Or can our teacher use this interference to adjust teaching decisions? So this is AI-oriented logic of this project. So This is a key architecture of the presentation. The first layer is about a data layer, including course performance, questionnaire response, and online behaviors. The second layer is the feature layer, where raw records are transformed into engagement features, outcome labels, and precipitation indicators. The third layer is AI analyze layer, which can support learning profile, risk scoring, correlation mining, and adaptive recommendation. The fourth layer is about teaching decision layer, where the teacher uses analytics output for pre-class diagnosis, in-class intervention, post-class feedback, and continuous improvement. This architecture turns a teaching model into a data-driven decision support system. And we also use BOPPP as models and online learning as an organization structure before class. Bridging objective and pre-assessment are implemented through online resources. In class, the middle part and the most important part. So participatory learning is conducted through case analysis, discussion, and presentation. So after class, post-assessment and summary are carried out by quizzes, review papers, and reflections. Therefore, the model is not only a teaching sequence, but also a data producing workflow for continuous improvement. So this slide shows about a quantitative result of learning performance. The average final course score was 88.33 with a standard deviation of around 5.8. The average course report score was 19.73 as the average review paper score was around 18.7. So these two tasks are important because they require students to search for information, synthesize course knowledge, and analyze engineering problems rather than simply recall isolated facts. Therefore, these results provide outcome evidence for the blended workflow. I interpret these findings as positive feasibility evidence at a course level. So, moreover, online task is also measured in this work. Only we can see the average precipitation rate is around 91%. So only a few students lack online test completion. So take completion can be used as an early warning feature. For instance, if a student has a low competition and a low routine score, we can prepare a target intervention for that student. And we also evaluate the course objective attainment. Course objective attainment was generously satisfactory with, we can see with all three objectives all around at a relatively high level. In addition, online participation was positively related to presentation scores, final paper scores, and perceived learning effectiveness. This is important for data-driven education because platform behavior provides process evidence. In future work, such data can be used for early warning, adaptive guidance, and target feedback. So the existing, our current data set, we can support a practical AI-enabled analytics layer without overclaiming an untrained deep model. But our data we get can support future AI-enabled teaching functions, including low attainment risk prediction and LLM-assisted formative feedback. So therefore, this study provides a data foundation and analytic workflow. Future work will train and validate predictive models using multi-concord data. So here is our work conclusions. So the three main conclusions are from aspect of data collection, learning entities, and AI-enabled future development. And we want to thank the Hubei Province of Teaching Research Project and the Teaching Reform Project of Wuhan University of Technology. Thank you very much for the listening. And any questions?
Thank you very much for your presentation. Any question, please?
I have one question. How can the
Yes,
method?
please. Yes,
How can
you
the
may ask.
method practically?
You are asking how can the method be used practically?
Yes.
Yeah, okay, thanks for your question. Because this method can enable the instructor use online behavioral signals to identify students with no engagement. So we can provide targeted resource feedback or early warning. So over time, the accumulated data can support a more automatic learning analytic dashboard for many engineering courses. Yeah, that's all. Thanks.
Thank you for your answer. Any more question, please? Okay, as I see, we don't have any new questions. So in this case, I would like to invite the next one presenter, which is a presentation number 3502. Is presenter here with us? Oh, yeah, I see. So please start your presentation. It's some delay, but we try to wait. Have some technical issues with your screen demonstration. Maybe you'll try to restart it, or maybe you have some problem with internet connection. Oh, as I see, the presenter is disappearing now. And he tried to re-upload, to rejoin us.
Oh, hello, can you hear me? Something wrong of my computer.
We can hear you, we see you. So try to launch your presentation.
Can you see my screen?
No.
No.
We see just a black screen. Oh, now it was good for a very short period.
Oh,
Again, have some problem. Oh, now we can see your presentation. Please start your presentation.
oh, can I see my screen?
Yes, yes, we see.
Yes.
Yes, you may start your presentation.
My Zoom has some wrong.
我用中文告诉你一下，你先点右上角的共享，再点上面这一排里边的放映。
右上角的共享。
你刚刚打开了后，右上角的共享，再点上方那一排里边的放映，再试一下。
We see your presentation.
Coding conversion。共享之后，它这边直接就死机了，我不知道是什么情况。
不急，慢慢来。
好，抱歉。
你就这样放。
哦，可以看到吗？现在
可以看得见，就这样放，好吧？一张一张的看。
好，Hello everyone, it's my pleasure to present our paper. 然后 in the next few moments, I will introduce our paper from above three aspects. The first part is introduction of the paper. The stock market is a crucial component of global financial system, providing platform for client and investor to trade stock and other assets. However, influenced by a complex interplay of factors, including economic indicators, financing report, global news, political events, and investor sentiment, the stock market exhibits high volatility and non-stability. Furthermore, investor activity, trade behavior, further drives short-term price fluctuation, adding to the market's complexity. The challenge lies in actually predicting the underlying mission drive change in stock market within their domestic and multi-dimensional interconnect ecosystem. In recent years, deep learning has demonstrated significant potential in quantitative trading and stock forecasting, offer new positivity for exciting the spatial temporal factor from complex financial data and aiding investment decision. Although with the development of deep learning, stock recommendation algorithm has achieved great success. However, the best measure of modern deep learning-based stock prediction solution suffer from two distinct shortcomings. First, most approach treat stock price motion as independent of one another price or rely solely on simplistic market model composed of private relationship with fair to constrain the complexity of real stock market. Secondly, temporal factors are insufficiently considered. Both stock prices and high other inter-stock relationships influenced by external and internal factors exhibit strong dynamic and in volume continuous over time. Therefore, a temporal modeling mode is necessary to accurately model the temporal efficiency of those multi-motional and high-order relationship. To solve this above problem, we precise our idea. We designed a novel framework to model three key mechanisms in stock investment focus, multi-focus driving high-order interaction and temporal dynamic. First, we have constructed a multi-relationship grid link stock and React entity based on temporal snapshot. In order to establish a multi-source relationship squad that influence stock prices. Second, we construct a shock hypergraph that based on a multi-relationship graph connect the stock node with high interdependence with hyper edge to model their collective pattern. Finally, we have designed a transformer based on alibi to control the temporal trends in stock price movement and the dynamic evaluation of multi-denomination in high-order interdependence over time. Completing the introduction to our paper, I will formally present our mode. An overview of the MHTSR model is shown in the figure, which primarily composition of four components. A multi-relationship graph construct, hypergraph convolution model, a temporal layer, and a prediction layer. The pressure formation mechanism is stock market influenced not only by dynamic internet transaction, but also by various external factors. It is therefore necessary to integrate additional market-related entities into a uniform framework in order to represent the relationship scored of stock market more comprehensively. Consequently, in our multi-relationship graph construct, we have explained the scope to include industry entity and investment banking entity and have construct a multi-relationship graph comprising those two types of entity and three types of relationship. In the hypergraph convolution model, we first construct the hyper edge based on group of stocks that show common attribution or driving across temporal snapshot of multi-relationship graph, thereby countering high-order interdependence that go beyond various interaction. We then use the LSTM to calculate the temporal dependence of each scores over the previous k day, which are sequentially constructed as the important input factor for each score. Finally, we aggregate factor from those higher-order structure via hypergraph convolution to generative representation of stock node in each temporal snapshot. In temporal law, we introduce an alibi-based transformer framework to capture the temporal illusion of stock mention information and its multi-dimensional higher-order relationship. Finally, in the prediction law, we use those temporal representation to predict future Scott returns. Finally, we show our modeling experiment. We construct experiment with two real-world datasets, NASDAQ QGIS and NYC, employing two common preference measures, the CIRR and the SR. In order to find the validity of the model, three kinds of experiment will conduct. The comparison with existing methods, the analysis of impact of each component, and the analysis of parameters sensitivity. First is the compared with existing models. In this part, we use 6 baseline algorithms as shown above. The explanation result as shown in figure. We can see that our model is superior to our baseline algorithm. We draw the following conclusion for the experiment rule. First, MHTSR construct hypergraph based on multi-relationship graph, enabling comprehensive integrate of multi-dimensional information, regret squad and their relationship entity. This approach considers the impact of various factors on the stock prices. Next, hypergraph convolution transcends traditional one-to-one relationship, enabling modeling of higher-order connection between stock and their susceptibility to collocation tensions. Finally, hypergraph snapshot capture stock relationship at a single point in time. The resulting stock factor sequence are fed into an alibi-based transformer framework to model the temporal evolution and of higher-order stock relationship, achieve a dramatic and comprehensive characterization of those complex connects. After that, we use two variants in analyzing the impact of different models. MHTSR, LSTM, the hypergraph convolution law and the temporal law was removed from the MHTSR model, constructing the struct factor representative solving through the designer LSTM-based law using historical sequence. MHTSR HGCN removes the temporal law from the MHTSR model and replace it with an MLP network. Significant after obtaining the stock factor sequence based on hypergraph convolution, we directly fed into the MLP law to output the fair factor. For the experiment result, we can see that the original model outperforms the two variants. In this section, we investigate the impact of some hyperparametry in the model, including the time window variety and the name of hypergraph convolution law. The result as shown in the figure. That's all. Thank you for listening.
Thank you for your presentation. And question, please. Yes, I see.
Hi, Chairs. I have a question.
Yes, please. You may ask.
Please, can you explain what a hypergraph is?
Oh, yes, I have. A hypergraph is the counterpart to simple graph. In the simple graph, edge can connect only two nodes. Whereas a hypergraph can link multi-node via hyper edge, thereby enabling the modeling of higher-order relationship between the nodes. That is why I use the hypergraph. I hope my answer will help you.
Oh, I know. Thank you.
Thank you for your answer. Any more question? Okay. In this case, thank you very much for your presentation, for answers. And now let me invite the next one presenter. Presentation number 3505. 3505. Yes. I see the presenter is with us. So please turn on your camera and start your presentation as well.
Honorable Chair, I cannot. Okay, this one.
Yeah.
Okay. Well, could you see my screen?
Yeah, we see your screen.
Okay. Okay. Hello, everyone. It's my pleasure to present the paper recommender system with integrated interaction expansion graph convolution. And I will introduce our paper from three aspects. The first part is the introduction of the paper. And with the rapid development of the internet time has produced a huge amount of information, to provide users with diversified choice at the same time, but often let the user lost in it. So it's difficult to get the information they need. The problem of information overload is becoming more and more serious. For recommender system as one of the main technologies to solve the information overload problem, can learn the user's preferences and the item characteristic based on the user's historical data and then accurately recommend the items to the user. Although with the development of deep learning, recommendation algorithms have achieved great success. However, any of the existing recommender system algorithms have some problems. For example, existing recommender systems often model the interaction information of the users and items through graph structures. However, because recommender systems often rely on user behavior to generate data, most users tend to interact with only a small number of items, thus causing the problem of data sparsity. To cope with the data sparsity problem, many researchers have proposed their own methods. DMGCF mitigates the data sparsity problem by dynamically constructing user graphs and item graphs to mine information between users and items. However, the interactive construction of user graphs and item graphs during the learning period incurs a large computational cost. And the HGCF models the original user-item interaction graph as a heterogeneous graph and constructs connections between similar users to achieve the data sparsity problem by mining the relationships between users. But how to determine the similar user threshold remains a challenging problem. To solve the above problems, we present our idea. First, we calculate the similarity between users based on historical user item rating data, and then estimate the missing rate values of users for the uninteractive items based on historical rating given by similar users, and then construct the interaction expansion graphs on the basis of original user item interaction graph. And the second, in order to effectively evaluate the importance of each graph in the user atom embedding space, we integrate an attention mechanism in the GCN information transfer process. The attention mechanism evaluates the contribution of each graph in the user atom feature embedding process, which in turn constitute the final representation of user and atoms. Finish the introduction part, we print the model. This figure shows an overview of the proposed method RIEG, which consists of three main modules. The first module is the graph construction module, which is the left part, and the second module is the embedded learning module, and the last module is the prediction and the optimization module. In the graph construction module, we compute the similarity graph between users based on their historical interactions. After that, the rating of the target users' uninteracted atoms are computed from the historical rating of the target using the user's top K similar users. It's worth noting that if the target users' top K similar users field provided a rating for an uninteracted atom, we keep the rating for that atom as 0. Finally, we construct the interaction expansion graph based on the computed rate of uninteracted atoms. In the embedded learning module, we model the feature representation of users and atoms through the constructed user atom interaction graph and the interaction expansion graph. The first one is use INT for abbreviation, and the second one is use EXP for abbreviation. Specifically, to model the high-order connectivity between user-atom interactions in the INT and EXP graphs, we stack multiple layers of GCNs to model the potential feature representation of users and atoms in the two graphs, respectively. The above figure shows the process of information aggregation process on the two graphs using the user as an example. Considering that users and atom embeddings from different graphs contribute differently to the final embedding of the user and atom, we integrate the attention mechanism in each GCN, which the user adaptively fills the user and atom embedding from the two graphs. And this figure demonstrates that the attention mechanism we have designed as an example of the user. After obtaining the updated representation of users and atoms in the training and prediction module, we link each layer of users and the representations as the final representation of user and atoms, and they input them into a fully connected network to output the final rating predictions. The use of a fully connected network rather than simple embedding an inner product is intended to enhance the ability of capture the nonlinear relationships between users and atoms in the prediction process. And this part we show the experiments. We elaborate the experiments on two real datasets, film trust and Doban, using two common evaluation metrics, RMSE and MAE. In order to verify the validity of the model, three kinds of experiments are conducted separately. The first one is the comparison with existing state-of-art methods, the analysis of influence in different phases, and the analysis of parameter sensitivity. And the first one is the comparison with SOAT. And the experiments is shown in this figure. We can see that our model is superior to our baseline model. We draw the following conclusion from the experiment results. First, the interaction expansion graph constructed based on the historical rating of similarity. Similar users can effectively predict the user's rating for uninteractive atoms, which can directly provide more interactive and effective interaction data from the modeling of the user and atoms, thus solving the data scarcity problem. And it's able to effectively evaluate the contribution of each graph in the user atom feature embedding process, which in turn constitute the final representation of user and atoms. We use two variants, IEG-EXP and IEG-ATT. And IEG-EXP means remove the interaction expansion graph constructor and the attention mechanism module from the whole model. And only use the GCN-based information transfer model. And the REG ATT means the attention mechanism model is integrated in the GCN information transfer model. It is removed from the REG model, and only a layer of full connected network is used to combine the user and atom embedding from the user-atom interaction graph and the interaction expansion graph. And from the experiment results, we can see the original model outperforms the two variants. And in this section, we investigate the impact of some hyperparameters in the model on the model performance, including the user atom feature embedding dimension D and the threshold K, and for the number of similar users during the construction of the interaction expansion graph, and the number of GCN model layer as L. And the results. Okay, that's all. Thank you.
Thank you for your presentation. Any question, please, for this presenter? Traditionally, we have at least one question. Okay, so in this case, thank you very much for your presentation. And now we switch to the next one presentation. Presentation number 3358. 3358. But I don't see presenter of this presentation with us. I don't see presenter. Okay, so next one, presentation number 3489. 3489. 3489 is here.
Okay, thank you.
We see you. You may start your presentation.
Can you see my screen?
Yes.
Okay.
Yes, we can see.
Okay. Good afternoon, everyone. I'm Liu Yanhui. I'm from Central College, Beijing University of Post and Communications. Today my presentation is optimization of PET bottle recycling network in CTA based on genetic algorithm. This is my presentation outline. It includes 7 sections. 1. Research background and motivation. Our research is motivated by the current policy context. China is vigorously promoting the circular economy and the dual carbon goals. However, significant research gaps remain. There is a distinct lack of targeted optimization research on PET bottle recycling. Our case study CTA is known as China Food City. It has a dense concentration of beverage enterprises and generates a huge amount of discarded PET bottles. However, the existing recycling system is dominated by scattered recyclers and small recycling stations. 2. 3-level reserve logistics network structure. We have structured a 3-level reserve logistic network. Level 1 consists of recycling service points responsible for collecting PET bottles from residential areas. Level 2 comprises transfer station, which aggregate and pre-process the collected bottles. Level 3 is the processing plant and conducting final processing and material recovery. 3. Cost composition analysis. The objective function consists of 4 cost components. Construction cost includes the building expenses of recycling service points, transfer stations, and processing plants. Operation cost covers site rent, employee wages, utilities, and maintenance. 3. Transportation cost is calculated as the freight rate multiplied by the two-stage transportation distance. 4. Carbon emission cost is the carbon emissions from transportation calculated at the trading price, minus the carbon benefits from recycled PET bottles. This design integrates economic and environmental objectives into a unified framework. This is our mathematical model, a multi-objective mixed integer programming model. The project function minimizes beta, which equals construction cost plus operation cost plus transportation cost plus carbon emission cost, and the 12 constrictions of the model. 4. Empirical data collection. According to the national and A province PET bottle recycling volume, we estimated the annual PET bottle recycling volume in City A. The cost of the 3 network service points include construction costs, monthly operating expenses, per kilometer transportation fees, and at all. 5. Node location determinations. We used MATLAB to process population raster data. We determined 57 recycling service points, 11 transfer stations, and 1 processing plant. The results are illustrated in the figure on the right. 6. Path planning and optimization results. The first stage routes are from collections from transfers. It includes 11 transfer stations and 18 routes. The second stage routes are from transfer to processing. It includes 2 routes from processing plant 1001. The environmental benefits of the optimization results are remarkable. Transportation carbon emissions are only 0.202910, while the carbon trading volume of recycled PET bottles is 0.2127 tons. 7. Conclusion. There are 4 main contributions. First, customized 3-level recycling network framework constructed for City A. Second, multi-objective mixed integer programming model established. Third, genetic algorithm with three-layer encoding proposed. Fourth, optimization scam verified. Okay, that's all. Thank you for your attention.
Thank you for your presentation. Any question, please? Oh, I see we have a question, so please ask a question.
Okay, Miss Liu, would you may I ask a question?
Yes, you may ask a question.
Okay, then does the carbon emission cost in your model account for the full life cycle carbon emissions associated with the recycling process, such as those generated during cleaning, crushing, and melting stages?
Okay, thank you for your question. So currently, our model focuses on transportation-related carbon emissions as they dominate reserve logistics. We adopt a carbon emission coefficient of 1.8 kilogram per kilometer and the carbon trading price. However, emissions from cleaning, crushing, and melting are not yet included. This is a limitation we aim to address in future work by integrating life cycle assessment. Thank you.
Okay, thank you very much for your answer.
Thank you for your answer. Any more questions? Okay, thank you very much again for your presentation. And now we have a next one presentation. I would like to invite the presenter with a presentation number 3491. 3491.
Good afternoon. Can you hear me?
Yes, we can hear you. And we see your screen as well. But with some black boxes.
Okay, can you see my screen?
Yes, we see your screen.
Okay. Good afternoon, respected chairs and dear colleagues. It's my honor to be here at the ICAILE 2026. My name is Liu Yijing, and I'm from Wuhan University of Technology. My presentation focuses on constructing a virtual peer instruction model based on constructivism to solve complex engineering teaching problems. The presentation is divided into 5 parts: research background, theoretical foundation, VPI model introduction, empirical research, and final conclusion. First comes the research background. Traditional engineering education has several obvious drawbacks as shown in the slide. It lacks real industrial engineering scenarios, and teachers cannot track students' complete thinking process. Courses pay too much attention to operational skills, but ignore high-order critical thinking training. Even if problem-based learning and traditional pure instruction have limitations, such as unequal student levels, single scenario setting, and delayed feedback. Therefore, we intend to build an AI driver VPI model that is virtual pure collaborative instruction to improve students' complex engineering competency. There are 3 threads to support our model construction. The first is the peer instruction raised by Professor Mother, which relies on equal peer communication, instant feedback, and cognitive conflict. Peer instruction provides core interactive logic for virtual peer design. Second is constructivism theory. It claims learners build knowledge actively rather than receiving information passively. which gets us to avoid students over-dependent on AI tool. Third is Bloom's cognitive taxonomy. There are 6 cognitive levels from memorization to creation. Our VPI targets high level such as analysis, evaluation, and creation to cultivate advanced engineering abilities. From existing literature, offline pure instruction is limited by small-scale application, while current virtual pure studies most focus on language and basic science. Fewer researchers design virtual pure systems for complex engineering critical thinking, which is exactly our risk. Now comes to part 3, virtual pure collaborative instruction model. Here is the definition of virtual pain in our context: an intelligent, interactive role that keeps fixed subject characteristics during multi-round task conversation. This is our VPI operation mechanism. It is a cyclic framework. 3 theories build the core, namely constructivism, peer instruction, and Bloom's taxonomy. There are 2 core participants in the whole process: educator and learner. The entire workflow forms a continuous cyclic iteration, enabling constant improvement of teaching and learning in the repeated rounds. Let's move on the details. Okay, first, teachers finish the pedagogical design, setting engineering tasks, and virtual pure interaction roles. Second, students independently complete the first draft solution V1.0 to reflect their actual metric. Third, students act as project managers and virtual teams play stakeholders. Complex and constrained prompt push learners to upgrade solutions to version 2.0 will repeat interaction. Fourth, learners conduct independent review following industrial standards and form the final version 3.0, effectively preventing over-reliance on algorithms. And finally, teachers score assignments and analyze dialogue reports to assess real learning performance and optimize subsequent teaching design in the next iteration cycle. The VPI model owns 3 outstanding features: customizable teaching scenarios, multi-level instant intelligent feedback, and simulated engineering conflicting conditions. We also built a three-dimensional evaluation systems based on Bloom's theory, covering basic engineering skills, engineering thinking ability, and human AI collaboration efficiency. And the software engineering's requirements analysis chapter is selected to carry out empirical research. The participants are 280 third-year computer undergrads. First score of the assignment is 20 points. We separate students into high, medium, and low groups and pick 15 samples from each group, adopting both quantitative statistics and qualitative coding analysis. The whole experiment contains 3 stages: independent analysis, virtual peer assisted revision, and final engineering evaluation. Here is our due evaluation framework covering 3 analysis dimensions. We combine quantitative data statistics and qualitative process observation together. There are 3 core analysis dimensions: instruction feasibility, competency improvement, and collaboration effect. Numbers measure overall learning outcomes, while qualitative content analysis students' interactive behaviors ensure our assessment is comprehensive and objective. Now we move to analysis conclusions. First is the quantitative feasibility round results. The average assessment score of 4 samples reaches 18 out of 20, with a median score of 19. Meanwhile, the 3-stage 4 completion rate is 95.56%, and the learners complete all 1.84 average dialogue rounds with virtual peers. These four indicators jointly prove that VPI model has outstanding practical feasibility in real engineering teaching. Let's look at quantitative data about competency improvement. Notable with the intergroup comparison based on intra-group ranking stability, we found that collaboration efficiency, namely interaction quality, serves as the core factor differentiating students' competency levels across groups. Interaction quality data show higher score students interaction more, but adopt less AI advance. This finding well explains why collaboration efficiency becomes the core factor of competency stratification we mentioned earlier. Here is our qualitative findings. Surprisingly, we observe students' cross-project engineering transfer and conflict identification skills, which also reveal obvious competency differentiation among groups. And qualitative conclusions are: first, all participants gain progress, and then high-level students can build standardized prompt and take charge of interaction, while low-level learners only put forward plan questions and rely heavily on AI. And to conclude, we constructed a usable VPI teacher model for complex engineering education and summarized two typical human AI learning models: critical absorption and passive following. In the future work, we will optimize the layered interaction rules and extend more curriculum experiments to perfect this model. And that's all for my presentation. Thanks for listening and welcome your questions.
Yes, thank you. I see we have a question, so may I ask a question, please?
Yeah. Here I have a question. Is there a unified standard to evaluate the quality of students' prompts?
Okay, thanks for your question. We evaluate prompts from 3 dimensions. Integrity of professor knowledge, structural rationality, and task pertinence based on Bloom's framework. And besides, we clarify to students that prompts directly reflected their mastery of course knowledge and serve as an important basis to assess their academic level. Thank you. Thank you.
Okay, thank you.
Thank you for your answer. As far as I understand, we don't have any more questions, so thank you very much for your presentation. And next, according to our scheduling, we have the presentation number 3406, but I don't see presenter for this presentation. So I would like to invite the next one. Next one, it will be presentation 3498. 3498, presenter is here with us. Please start your presentation.
Okay. Can you see my screen?
Yes, we see your screen. You may start your presentation.
Okay. Good afternoon, everyone. Thank you for being here. I'm Yang Yan from School of Transportation and Logistics Engineering at Wuhan University of Technology. Today, I'm honored to present our research on the AI-driven whole process intelligent teaching management model for top innovative talents in transportation majors.
Let me briefly outline today's presentation. We will cover 4 main sections. Let's begin with the introduction and background of this research. Our research is motivated by several important national policy initiatives. Against this backdrop, transportation-related disciplines must proactively respond to the transportation powerhouse shortage. Therefore, the objective of our research is to construct an AI-driven whole process intelligent teaching management model that achieves precious talent selection, personalized development, and comprehensive evaluation. Let me briefly describe the current status of transportation majors. Many universities have established specialized elite engineer classes for top innovative talent selection. These programs integrate AI plus and transportation plus concepts to optimize teaching resources and reconstruct curriculum systems. They also build interdisciplinary teaching resource libraries to establish multi-dimensional competency evaluation models. Now, let's move to the second part, analyzing and their key challenges in traditional teaching process management. Our analysis identifies 3 core challenges in traditional teaching management. First, regarding training program revision. Second, at the operational level, existing course selection models, lack AI-powered tracking. Third, their evaluation system, traditional systems failing to assess students' comprehensive development. Having identified these challenges, let me now present our proposed solution. Our research proposes an AI-driven approach that integrates artificial intelligence, big data, and cloud computing into the entire talent cultivation chain. The model consists of 4 core modules. The ultimate goal is to innate information science and enhance the digitalization level and the scientific rigor of teaching management. Let me elaborate on the first module, Talent Training Program Revision. We propose reconstructing training objectives to shift from single discipline knowledge acquisition to the cultivation of interdisciplinary and cutting-edge innovative talents. The second and the third modules address teaching and personalized management. For diversified teaching, we promote flexible modes, including blended learning, flipped classrooms, and seminars. For personalized management, we adopt a student-centered OBE approach. The fourth module is the multi-dimensional talent evaluation model. We propose a 3-dimensional dynamic capability evaluation framework. The cognitive development, the thinking advancement, and the innovative potential. The comprehensive score is calculated as a weighted sum of these 3 dimensions. Furthermore, we establish a closed-loop evaluation, diagnosis,
intervention mechanism. To validate our model, we conducted a case study with 10 students from transportation-related majors. This table shows the three-dimensional evaluation scores and the comprehensive rankings. As we can see, the three-dimensional scores reveal distinct capability profiles for each student. Based on the closed-loop mechanism, we identified each student's weakest dimension and applied targeted interventions. The bar chart on the right composite scores before and after intervention. As shown, every student exhibits measurable improvement, with the most pronounced gains observed among low-performing students, such as number 4 and number 8. This confirms that our model effectively prioritizes resources towards those with the greatest developmental need. Verifying the effectiveness of the closed-loop evaluation diagnosis intervention mechanism. Let me conclude with our key findings and future directions. First, AI-powered intelligent management models have emerged as a core driving force for educational innovative in the digital era. Second, the quality of cultivating top innovative talents in transportation directly determines the industry's future prospects and core competitiveness. Third, our AI-driven whole process intelligent management model achieves precious talent selection, personalized development, and deeper industry integration through this more module collaborative ecosystem. For future work, we plan to establish a long-term tracking mechanism to collect employer feedback, construct an AI-enabled closed-loop feedback mechanism for continuous optimization, future deepen AI and transportation interdisciplinary integration, and extend this framework to broader engineering education domains. Thank you very much for your attention. I would be happy to take any questions.
Thank you for your presentation. As I see we have a question, so you may ask a question, please.
Okay, I have a question. I want to know that what are the most significant practical challenges in deploying this framework? How do you assess its feasibility for the adoption by other institutions?
Thank you for your question. We acknowledge two major categories of practical challenges. First, faculty capacity building. Effectively leveraging AI early warning alerts and personalized intervention recommendation requires basic data literacy among teaching staff, which necessitates dedicated training programs. Second, data ethics and privacy collection and use of student behavior data must comply with rigorous ethical standards, ensure informed consent and data security at every stage. Regarding generalization, our module designs a key
advantage. Institution can begin with a single module without full system development. This significantly reduces initial costs and technical barriers. We also plan to select 2 or more institutions with varying resource levels for cross-institutional validation in future studies to systematically assess adoption feasibility. Thank you.
Okay, thanks for your answer. I understand it. Thank you.
Thank you for your question.
Thank you. Any more questions? As I think we don't have new questions, so thank you very much for your presentation and answer. And we have to switch to our next one presentation. I would like to invite Zarina Poberezhная. This is presentation number 2622. Zarina, are you with us?
Yes, hello, good day. Yes, one moment. I open my presentation.
Yes, we are waiting.
Moment. Do you see my screen? Do you see my presentation?
Yes.
Yes, you see your presentation. You may start your presentation as well.
Okay. The topic of our presentations is artificial intelligence tools in the system of optimization logistic process for transport enterprises. The main topics of outline is introduction, methods and materials, results and discussion, conclusions. This study is
Sorry, you turn off your microphone. Please turn on it. We don't hear you. Your microphone is off. In the left bottom of the screen, you may check the red one label. Oh, I think now it's very good.
Okay. Do you see my presentation?
No, this is something else. Now we see a presentation.
Okay, moment. Maybe I can. Just a moment. Now you see my presentation. Do you see my presentation?
Yes. Everything is good.
Okay. The main paper outline is introduction, materials and methods, results and discussion, conclusions. So, in modern business conditions are characterized by high level of uncertainty and increasing demands for the quality of service provisions. The transformations of logistic routes due to border closures, military operations, pandemic, and other changes in the global environment pose challenge for enterprise and respond quickly them and adapt to new requirements. For transport enterprises, increasing transportation volumes and complicating logistic routes require optimizing logistic process. That's why the use of AI tools in optimizing logistic process allows improving the management process quickly, responding to change in supply chains, tracking the locations of goods in real time. The use of AI technologies in optimizing logistic process of transport enterprises is an important tool for innovating development as it allows planning operation process, optimizing inventory levels, and determining resource, predicting consumers' behavior, preventing storages, and so on. The purpose of the study is to analyze the effectiveness of using AI tools in the system of optimizing logistic process of transport enterprises. So the materials and methods of our paper will be to characterize the main artificial intelligence tools and their advantages and capabilities for optimizing logistic process of transport enterprises. Do you see in the table 1? For example, you have some AI tools, machine learning, deep learning, and so also advantages and opportunities you will be to use of these tools. Despite significant advantages and prospects application artificial intelligence tools in management logistic process transport enterprises, they using a combined certain restrictions and availability narrow places in table 2. You see limitations, complexity implementations, quality competences data, uncertainty system behavior, and other. And also you have to see in this table descriptions, impact on management logistic process for each is limitations. Successful of use AI in logistic process, it's necessary to develop a comprehensive approach taking into account technical, organizations, and personal aspects that significantly change, among of which reduction of in acceptance time managerial solutions, optimizations routes, planning, rational using resources, close interconnection and communications between subdivision enterprise, ambulance reaction enterprise for changes, external environment and minimization risk, adaptation, logistic process to change. On these pictures, you can see the main traditional logistic process in transport enterprise. You have some 6 stage: receipt of order, transportation planning, transportation and cargo preparation, monitoring, and also evaluation and adjustments. But if you use some AI artificial intelligence tools, you have seen more modifications logistic process with using AI tools. On these pictures, you have some 7 stage. For order reception and automatic process, demand forecasting and data analysis, automated routes, transportation and cargo preparations with digital controls. These all stages will be automatically, and to reduce human influence of this transport of the logistic process. It will be great, and also will be efficiency for logistic company. In the results of our study, we decide to present mathematical model for assessing the efficiency of logistic process and transportation enterprise was developed in AI tools. For example, for empirical analysis, we based 3 logistic companies: Schenker, Kühne-Nagel, and DSV Logistic Company. The panel has the following structure. For example, 3 enterprise and time of periods, and also 72 observations. We have some formula will be used, integrated indicators, level of AI usage, data quality, level digitalization, human factor, and random error. After that, we initial data of the model for use the formula to, and we use the weight coefficients for model determining the explained methods. And model results, we have some weight factors of transportations enterprise for each company, for example, Kühne-Nagel, Schenker, and DSV Logistics. The results of our modeling you will be see in this table. Simulations results we have with using AI and efficiency of logistic process. The figure 3, it will be empirical regressions dependent of efficiency on the level AI use. We have C rating and standard row. So after we based results of statistical diagnostics of the model and following conclusions, and we have 3 stages. The distributions of model residual is normal. At the 5 significant level, heteroscedastic is not confirmed. The absence of a pronounced systematic pattern around of the figures 4, you see the comparison theoretical and empirical model for enterprises. The have some basis of functional model, impact of AI, and efficiency components. And we decide that if you used AI tools, enterprise will be more automatically the process and will be efficiency is increased in the future. So like conclusions, we want to say that logistic process performed by transport enterprise basis the efficiency functional. Them are less effective because they are focused on central management and human factor. But if enterprise will be use AI tools, it will be more coordinations, and for enterprise it will be to access and success in the future. So AI tools and digitalizations in general allows to increase the level of competitiveness and stability in the market for enterprise like transport enterprise or another enterprise for others. Thank you very much.
Thank you for your presentation. And now, any question for the presenter? Oh, I see we have a question, so you may ask a question, please.
Okay. I want to know that your simple consists of the only 3 large international logistic enterprises. How do you address the potential limitations of such a small cross-sectional simple, especially regarding the generalizability of your findings to the broader logistic industry?
Thank you for your questions. Yes, we make some regressions and we have some informations in statistical data of the enterprise. So we used financial data of this enterprise, and we made this model for this enterprise concerning the data of volumes this enterprise, for example, transportations volume, delivery time, expenses, quality data, but our empirical regressions depend of efficiency on the level AI use, and the distribution of this model it will be diagnostic of this enterprise indicators. We have some indicators enterprises, and after that we weight these indicators and make some simulation model for using and to see some efficiency enterprise before traditional transportations and with using AI tools transportations.
Okay. Now, thanks for your answer.
Yeah, thank you.
Thank you for your answer. Any more question, please? Okay, Zarina, thank you for your presentation, for the answer on the questions.
thank you for your invitation in your conference. I will be happy to see you in this conference because for me it's first time I to enjoy in your conference. But I'm very happy because I see today very interesting and very most scientific discussions and scientific topics. And I think in the next conference I will be also with you. Thank you.
Thank you. Thank you.
Thank you for your warm words for our conference. Okay, thank you very much again. So next one, I would like to invite Yuri to present his paper. We have just 2 presentations left, and the first one will be presentation of Yuri Gavin.
Yeah, thank you very much. Let me share my screen. A second, please. I guess you should see my screen now, right?
Yes, I see it.
Yeah.
Yeah.
Thank you very much. Okay, so hello again, and today I'd like to present our research titled Deep Learning Models for Identification and Classification of Military Equipment from Images. So recent advances in computer vision and deep learning have significantly improved automated image analysis. These methods are widely used for object detection and classification, including military applications. However, armored vehicles, especially tanks, are difficult to classify due to different reasons: high visual similarity between models, small structural differences, variation in lighting, viewpoint, and image quality. So classical machine learning methods are not robust enough for such tasks, while deep learning offers better performance, but still faces generalizations challenges. So our motivation and the problem that we are solving is the following: poor performance on fine-grained classification tasks, lack of hierarchical data. Most models are designed for general object recognition and fail to distinguish subtle differences between tank modifications. Aim of the study. So the aim of the study is to develop a deep learning-based system for automated identification and classification of military vehicles. The system should identify the base tank type, determine the specific modification, and remain robust under real-world conditions. So the key idea to design a complete hierarchical recognition pipeline, not just a single image classifier. So the following slide is about literature. So yeah, literature review shows that convolutional neural networks CNN are still highly effective for image classification tasks, and architectures such as ResNet, EfficientNet, and MobileNet are often used with transfer learning. This is important because collecting large military data sets is difficult. And military-specific studies highlight challenges: data set imbalance, lack of standard benchmarks, and low robustness in real conditions. So formally, we define the data set as a set of input images, and the classification function maps each image into 2 levels of labels. The first level is the base tank type, and the second level is the modification. So the structure is important because a modification should be interpreted as a part of specific vehicle family. The main challenges are highly visual similarity, limited and imbalanced data, hierarchical class structure, and the need for practical deployment. The data set was constructed from publicly available images of military vehicles. At first, images were organized by a specific modification, and then they were grouped according to the base tank type, while modifications were preserved at the second classification level. The data set has a long tailed distribution, meaning that same classes have many images, while others have only a few. To improve training stability, underrepresented classes were filtered out. The dataset was split into 50% for training, 30% for validation, and 20% for testing. Our system architecture is the following. So the proposed system uses a client-server architecture. The client side is implemented with React. It provides the user interface, image upload, and request handling. So we don't have just some backend pipeline, but the full application implemented with front-end and backend. The server side is implemented in Python using PyTorch. It processes the image, performs model inference, and returns the classification result. Communication is organized through a REST API. This architecture provides modularity, scalability, and easier integration into web or cloud environments. What models did we use? So for the experiments, we used two pre-trained convolutional neural networks architecture, ResNet 50 and EfficientNet B0. So the first one uses residual connections, which help train deeper networks and extract more complex visual features. And the second one is designed to balance accuracy and computational efficiency. Both models were fine-tuned using transfer learning for military vehicle classification. The training pipeline included image resizing, normalization, tensor conversion, and image folder-based dataset loading, as usual. We used a custom training loop to control forward propagation, loss calculation, backpropagation optimization, and validation. Several techniques were used to improve generalization, like mix-up and cut-mix augmentation, focal loss for class imbalance, learning rate scheduling, and gradual unfreezing of layers. These techniques were especially important for the second level classification plan. As I said before, the first layer is to classify the main classes, and the second one is to find modifications of some particular class. So our training results show that both models demonstrated stable convergence, and ResNet 50 improved faster and reached higher final performance. By epoch 100, it achieved 94.66% training accuracy and 85.65% of validation accuracy. EfficientNet B0 also improved, but its final validation accuracy was lower, as you can see on this slide, 78.26%. The best performance was achieved after approximately 80 to 100 epochs. Here we can compare these two models, and the difference is not very large, so both models are effective for recognizing primary tank types. However, ResNet 50 demonstrated slightly better accuracy and robustness, especially when distinguishing visually similar classes. That is really important for our task. EfficientNet B0 can still be useful for simpler classification tasks, but the first one showed a better overall balance. Precision recall analysis. This analysis shows that Abrams, so the name of the tank, and Leopard 2 were recognized with the highest accuracy. Lower performance was observed for T64, T72, and T80 families because these classes are visually similar and include many related modifications. That are the problems for our common approaches. And ResNet 50 showed better class separation. EfficientNet B0 had higher recall in some cases, but also showed more confusion between similar classes. The second level classification is much more difficult. For tank modification classification, ResNet 50 achieved 21.43% accuracy, while EfficientNet B0 achieved only 13.10%. This performance drop is mainly caused by strong visual similarity between modifications and the limited number of training samples. The confusion matrix analysis showed that efficient net B0 tended to overpredict dominant classes, whereas net 50 produced more balanced predictions, but the overall accuracy was still limited. So key insights were obtained from the experiments, and they are the best learning rate was 0.003. A batch size of 16 was the most effective for fine-grained classification. Partial unfreezing after the 20th epoch improved accuracy by approximately 2 to 5%. Mix-up and cut-up mix also improved generalization by increasing training data variability. So now let's talk a bit about summary of results. To summarize, both models performed well at the first classification level. ResNet 50 achieved 79.64% accuracy, while EfficientNet B0 achieved 78.12%. At the second level, accuracy was much lower, 21% for the first model and 15% for the second. Overall, ResNet 50 was more stable and more robust to visually similar classes, and the second model was more suitable for simpler base level classification. And to conclude, the study addresses the problem of automated identification and classification of military equipment from images using deep learning. The proposed approach uses a hierarchical classification strategy with two recognition layers, levels, base vehicle type and specific modification. The main contributions are a structured dataset preparation method, a two-level classification framework, and the client-server system based on React, Python, and PyTorch. We also experimentally compared two models and under limited and imbalanced data conditions. And our future work will focus on attention mechanism, multi-scale feature fusion, specialized fine-grained recognition architectures, and expansion of the dataset with more annotated samples and additional vehicle classes. Thank you very much. Maybe you have some questions.
Any question, please? Yes, you may ask a question.
Okay. Thanks for your speech. I want to know that the problem mentions sensitivity to dataset imbalance and limited data. What strategies have you adopted in your study to mitigate these issues?
Yeah, thank you very much for your question. So, to reduce the impact of these limitations of limited and imbalanced data, we used several strategies. And the first one is we organized the dataset hierarchically, grouping modifications under the base 10 types. Second, we removed classes with too few representative samples to avoid unstable training. And the third step was to use transfer learning with pre-trained two models that I mentioned today, which is useful when the dataset is not very large. Also for fine-grained classification, we applied focal loss to give more attention to difficult and underrepresented classes. And we use also mix-up and cut mix, as I mentioned before, augmentation to increase data variability and reduce overfitting. Learning rate and gradual unfreezing were also used to make fine-tuning more stable. Thank you very much for your.
Okay, thanks for your answer. I understand it.
Okay, thank you. Thank you for the answer. As far as I understand, we don't have any more questions, so thank you very much for your presentation. And now we have a last one presentation in our stream. This is presentation number 2634. Ivan Izonin will be presented, so I give you the floor for this presentation. We see your presentation on the screen now. Please
Thank you very
restart
much.
it. Please restart it because we don't see your presentation. And now we see again.
Thank you very much. Dear colleagues, I would like to present the results of our research methods for selection-based models in stacking ensembles using prediction and error diversity measures. Authors are Ivan Izonin, Nazar Savitsky, Roman Tkachenko, Michal Kovac, Krystyna Zub, and Roman Muzyka. I am Ivan Izonin, professor at the Department of Artificial Intelligence of Lviv Polytechnic National University. I obtained Doctor of Technical Science degree in 2025 in the specialty System and Means of Artificial Intelligence. Also in 2016, I obtained a PhD degree at the same specialty. Also, I have a master degree in computer science and master degree in economic cybernetics. The public profiles you can see on the slide. Currently, I am working at the high-speed computational intelligence lab. Our lab focused on the development new non-iterative neural and neural fuzzy system for different application areas. My primary scientific interests are small data analysis. About this research. Stacking, it is an approach when we try to combine different machine learning algorithms or artificial neural network in one system, where the result of each combined basic models create a new data sets for meta algorithms. In this case, we usually obtain a higher accuracy in comparison with each based model that taking part in the stacking. And we obtain more trustworthy solution for medical doctors, for civil engineers, and other experts in different domains, because in this case, the decision was taken not from one model, but from several models. But the predictive capacity of stacking ensembles depend not only on the accuracy of individual models, but also on their diversity and complementarity. In practice-based models are often selected intuitively, without a quantitative assessment of prediction and error similarity, which may lead to structural redundancy. Redundant-based model increase training and inference time. And therefore, the aim of this paper is to improve the efficiency of stacking ensembles through the quantitative selection of complementarity-based models, reducing ensemble complexity while maintaining or even increasing predictive performance. If you check scientific literature on this topic, you can see that most of the authors that try to create a stacked model use some heterogeneity-based selection that assume diversity without quantitative verification, or accuracy-based selection that ignores complementarity and diversity. The authors try to build stacked ensemble based on their knowledge of the machine learning algorithms or artificial neural networks that they are trying to include in the stacking. More advanced approaches use correlation-based selection, but these methods considers only one aspect of the model similarity, or diversity measure-based selection, but such models usually relies on a limited set of heterogeneity indicators. And the last one direction is optimization, but this approach often computationally expensive for large ensembles. Therefore, the main limitation of existing methods is that they typically evaluate only individual aspects of diversity and do not provide a comprehensive assessment of model complementarity in stacking ensembles. We try to solve this problem using different diversity indicators. We use, in our approach, we use predictive correlation, error correlation, normalized error difference, and error covariance. Each of these indicators try to evaluate different results of different basic models from different perspectives. And the combined use of such indicators provide us the ability for the comprehensive assessment of model heterogeneity and complementarity, and we can build a more effective stacking ensembles. To evaluate this for indicators, we use heuristic procedure for base model selection. On the step one, we try to include a model with a low prediction accuracy. On the second step, we try to calculate these all indicators. On the third step, using graph methods, we try to select base model and build our stacked ensemble. For the modeling, we use open access datasets, medical personal cost datasets from Kaggle platform. Information for it you can see on the slide. For experimental validation, we use out-of-fault validation procedure, different performance indicators, and also we taking into account the inference and training time. The results of our approach you can see on the slide. Full stacking models, it's a stacking model that use 10 machine learning algorithms. Reduced stacking model, it's our model built on our approach using diversity and error indicators. And this model has only 3 machine learning algorithms. It's a decision tree, his gradient boosting, and k-neighbors model. As you can see, we obtain almost the same or sometimes better accuracy using 3 machine learning algorithms in comparison with full stacking models. But we significantly decrease the training and inference time. As a result, in this paper, we developed a method for selecting base models in stacking ensembles based on prediction and error diversity indicators. Using our experimental evaluation, we can say that obtaining result demonstrates that our approach is effective for reducing structural redundancy and computational costs while maintaining acceptable prediction quality. Thank you for your attention.
Thank you for your presentation. And now, any question, please, for the presenter? Yes, I see we have a question, so you may ask a question.
Okay, thank you for your speech, and I want to know that you mentioned using prediction correlation, error correlation, normalized error differences, and error covariance to assess the model similarity and complementarity. Could you explain how these 4 indicators work together to form a comprehensive evaluation framework?
Thank you for your question. For this purpose, we can use existing methods, but we develop some our heuristic procedures that I told you in our presentation. You can see it on the slide. On the first step, we try to filter the models that don't provide acceptable prediction accuracy. On the second step, we doing conflict analysis. On the third step, we build conflict graph, try to include or exclude the models that has some conflict according to our indicators. And on the final step, we choose the models that are acceptable for our approach. Thank you.
Okay, I understand it. Thank you very much.
Any more questions? As I see, we don't have any new questions. So thank you very much for your presentation, for the answer on the questions. And dear attendants, dear colleagues, dear authors, that was a last presentation in our section. So our conference is going to be finished. It's going to be finished. In order to make some conclusion remark, I would like to give a floor to speak several words to the Professor Katy Zhang. As conclusion, please, several words as conclusion.
Thank you. Hello, ladies and gentlemen. I'm so happy to announce that our international conference, ICAILE 2026, has been successfully closed. Our conference, Artificial Intelligence and Logistic Engineering, realized a gathering of scholars from different countries and regions, from different academic fields, set a platform for mutual exchange and learning. We've got 4 keynote speakers to give their wonderful presentation to the attendees. More than 60 authors have speech at the conference, sharing their team's research results and experiences. And everyone interact and exchange ideas. This is a great experience and a process. As a co-chair of the conference, it is a great honor for me to meet so many researchers and friends through this platform of our conference. I cherish this opportunity. I hope and believe that everyone has got a great enjoy in this process of communication. Thank you all. See you later and see you at our next conference. I have to say goodbye. Thank you.
Thank you very much for your words. Also, I'd like to speak several words as conclusion, as closing remark for our conference. It is my personal great pleasure to be chair for the closing ceremony and for the entire conference. I would like sincerely thanks to all speakers, authors, attenders for their valuable contribution, active participation, generating a question and answering on this question. This conference provided a very strong platform for the sharing, innovating ideas and advancing research, especially in the artificial intelligence and the related fields, practical related fields. So we look forward to meeting you again on the next year in our conference. My best wishes to all participants and all the best for the all. Thank you.
Thank you. Thanks, the chair, for your hard working. Thank you.
Thank you.
It's my pleasure.
Bye-bye.
It's my pleasure.
Okay.
Bye-bye.
See you next time.
Bye. Bye.
Thank you very much. See you next time. Thank you very much again for
See you next
all.
time. See you. Bye-bye.
Thank
Bye.
you.
Bye.
Thank you. Thank you, everyone.
2026 has been successfully closed. Our conference, Artificial Intelligence and Logistic Engineering, realized a gathering of scholars from different countries and regions. 郑斌是要先关